a planet that has captivated humanity for centuries, a world of mystery, myth, and scientific pursuit. Mars, the red planet. Once thought to be Earth's twin, Mars has ignited imaginations with visions of ancient civilizations, towering mountains and vast canyons carved by forgotten waters. But beyond the legends lies a planet with a history more dramatic than we ever imagined. From the colossal Olympus Mons, the tallest volcano in the solar system, to the enigmatic polar ice caps hiding secrets beneath their frozen layers, Mars is a time capsule of planetary evolution. Today, robotic explorers trace its ancient riverbeds, searching for clues about a time when Mars may have been alive. But what did they find? Were there ever oceans? Could Mars have once harbored life? And most importantly, could it still? With new discoveries reshaping everything we thought we knew, the story of Mars is only beginning. This is the exploration of a lifetime. Prepare to witness Mars like never before. Mars constantly excites and intrigues us, whether seen as the simple red dot in the sky by our ancestors, or the planet traveled by modern robots in their exploits. Once considered Earth's sister planet and a possible habitat for extraterrestrial life, Mars has often been the subject of too much conjecture and little research. Recent studies have exposed the planet's real features, dispelling many old legends. Unexpected elements brought by recent discoveries make Mars an even more appealing place than hitherto believed. What new perspectives have the Mars probes given us? Like Earth, Mars is a complex and vast sphere with a long past. This book will support these ideas by delving into the core of contemporary planetary science and tackling its ambiguities and occasional certainty. We show a large selection of pictures, including some hitherto unpublished ones. Although Mars is a fascinating place, a book on it shouldn't only be a visual feast. As we reveal this new universe, which is distinctly extraterrestrial, despite having many parallels on our planet, the images will act as markers. Let's investigate Mars's unique qualities. Above 20,000 meters, Olympus Mons is the biggest volcano in the solar system, and picture yourself at its foot. Then picture the polar glaciers, which are made of many tiny layers that show past fluctuations in temperature. Whereas odd dunes tell the story of the winds that created them, the Great Plains show the marks of catastrophic flooding. These are only a few unique qualities that make Mars a planet of ongoing fascination. Imagine one day on Mars. Nocturnal frost gives way to mists and fogs as morning breaks, revealing the orange sky. Dust devils sweep the ground during the hottest part of the day. A little, irregularly shaped moon wanders the heavens for hours at twilight. As it does sometimes during winter, will a global dust storm sweep over the Earth tomorrow? Beyond its breathtaking scenery, Mars reveals the planet's workings and provides a fresh field of study. Important questions include understanding Mars's formation, the causes of its different evolution from Earth, and the historical insights its geology offers. Could life have existed there? Is it now there? Which processes now affect Mars? These fundamental components make knowledge of Mars necessary to grasp our roots. Of all the planets in the solar system, Mars most closely resembles Earth. Geologists, meteorologists, and many other scientists have a large laboratory to assess their knowledge of the events on terrestrial planets. Mars has the benefit of keeping traces of its past. By contrast, the Earth lacks this benefit. The surface of our planet is always changing. Plate tectonics and erosion have erased the records of 4/5 of Earth's past. There are few hints about the state of the Earth when the first microorganisms developed before the broad use of carbon chemistry. Mars can clarify the beginning of life and arouse our past. Understanding Mars is like understanding our own beginnings. As we investigate Mars, we must pay tribute to the unwavering efforts of many engineers and researchers worldwide. Their common goal is to realize the next Mars missions. Over the past decade, over 10 space probes and their robotic explorers have been sent to the Red Planet. In the next years, more missions from Earth to Mars will be sent. Fresh probes will be sent, and samples of Martian surface material will be collected. People will also travel. Mars exploration is an ongoing, changing activity yielding fresh ideas and discoveries. Enhanced by the great images and data from Mars Express, the first European probe, and NASA's robotic geologists, the relentless Mars exploration rovers. This video series thoroughly summarizes our current knowledge of Mars. Scientists need a temporal framework to classify the observable formations before fully examining a planet's geophysical development. How might we date Martian landscapes without surface samples? The answer is in counting craters produced over long periods by arriving meteorites. This idea drives all the dates for geological structures mentioned in this book. Early after its formation, 4.5 billion years ago, meteors constantly bombarded Mars. The intensity continued until 3.8 billion years ago. As the number and size of impactors dropped, this process also progressively dropped, stabilizing during the last billion years. The density of craters on the surface per unit area allows geologists to create a relative chronology. The lower frequency of strikes across time makes this possible. Often mentioned, especially in Part 2, the extensively cratered plateau of the southern hemisphere has many large craters of great depth. Any softly cratered surface, such as the plains of the northern hemisphere, must thus come before it. Still, counting craters offers just the relative age of one site against another. While the southern high plateau is clearly older than the northern plains, its exact age depends on surface samples from Mars to evaluate its radioactivity for dating needs. Future space missions will do this, even if retrieving the priceless samples is impossible. The Apollo astronauts' retrieval of lunar samples concurrently drives planetologists to use a shortcut approach. Our natural satellite features a cratering curve. The lunar samples calibrate this curve by substituting absolute dating for relative dating, using samples from the Moon and adding correction factors that consider things like Mars's position relative to the Sun, its gravity and its atmosphere, among other things. Researchers who study Mars have been able to make accurate predictions about the ages of various areas on the planet. Although there are some minor variations in the exact estimates depending on the values given to the adjustments and the models used. This extrapolation works sufficiently for our needs, since we do not have a better approach. Mars's history begins in the shadows of the past, when hardly any of the solar systems we know existed. Not even the Sun. But the universe was already old. Perhaps 10 billion years old, 2/3 of its present age. Eventually, all the components creating the Sun, Mars, Earth, and life forms hung suspended as gas and dust. Over millions of years, the solar system suddenly emerged on the cosmic timescale. Events later would irreversibly determine the destiny of the red planet. Mars mostly consists of heavy chemical elements, including oxygen, magnesium, silicon, and iron. Just like the other terrestrial planets, Mercury, Venus, and Earth. These atoms did not come from the Big Bang. The singularity, marking the beginning of the universe about 13.7 billion years ago. This primordial explosion produced the lightest elements: hydrogen, helium, lithium, and deuterium. From what source do the elements that form planets come? Early ideas suggested the sun created the heavy elements seen in planets. The Greek philosopher Anaxagoras, 500 to 428 BC, is thought to have first proposed this idea, since he claimed that iron meteorites proved the sun was only a mass of red-hot iron. Although the sun consists of hydrogen and helium, the idea that it provided the components for planet formation is not totally unrealistic, since heavier elements are found in it. Moreover, their concentration is similar to primordial meteorites forming planets. Like in these meteorites, carbon atoms abound in the sun at 11 times the count of silicon atoms. Still, the idea of a solar origin for the planets raises a major challenge, since it cannot account for the variations in the abundance of light elements, especially deuterium, lithium, and boron. Whereas planetary material does not show this deficit, the sun lacked some elements at the time of planetary formation due to their consumption during fusion events. A phenomenon still present today. Today, our study of ancient solar system meteorites helps us offer a more complete solution for planet genesis. The explosions of large stars following their life cycles provide the heavy elements found in the sun and its planets. Having turned all of its hydrogen into helium, a star generates heavier elements as it approaches the terminal phase of its life. Helium is transformed into carbon, oxygen, and nitrogen, which develop into even heavier elements as fusion events continue. This process ends in a supernova explosion in sufficiently massive stars that drives all these components into space. They will then help to create new stars and planets. The sun started to shine in a disk of gas and dust some 4.52 billion years ago. The temperature was just high enough to let water and other volatile compounds exist in a gaseous form. Only low volatility compounds, such as silicon oxides, magnesium, and metallic elements, could keep a solid state. Porous agglomerates around 1 meter in diameter were produced by interactions and bonding of dust particles. These bodies collided until they created kilometer-sized planetesimals, the basic building blocks of future planets. After a quiet infancy, the sun entered a turbulent adolescent phase about 10 million years of age. Gases and volatile compounds turned around and started to travel backward for the first time since birth. Powerful particles flow from the sun's corona, called the solar wind, and drive them outside the solar system. Water vapor drifted toward lower temperature areas as the matter was distributed. 5 times the current distance between the Earth and the sun. Water vapor condenses into ice particles some 820 million kilometers from the sun. Tens of times more massive than Earth's current mass. The ice blends with dust to form a planet. The gravitational field of this enormous entity drew significant volumes of hydrogen, which produced Jupiter during a span of less than 10 million years. With its orbital period double that of Jupiter, Saturn needed twice the time to develop at a distance from the Sun, about 1,250 million kilometers. Originating under similar conditions, Uranus and Neptune consumed icy planetesimals at a distance from the Sun more than twice that of Saturn. Near the Sun, planetesimals continued to attract and crash into one another. Embryonic planets evolved into the smaller planets of the young solar system within 10 million years. About 7,000 kilometers in diameter, several were the same size as Mars. Some resembled Mercury, 5,000 kilometers. Many others matched our moon's 3,500-kilometer diameter. The modern component of solar system history started between 4.47 and 4.44 billion years ago. During the last catastrophic collisions between planets, Earth and Venus accumulated the most readily accessible elements. A planet about the size of Mars had crashed against Earth. This influence created the Moon. Jupiter then moved toward the Sun, producing Saturn, Uranus, and Neptune moving further apart. The planets have kept their present orbits since that time. The terrestrial planets, Mercury, Venus, Earth, and Mars, were a jumble of planetesimals. Today's planets show an iron core surrounded by a less dense rocky mantle and covered by an outer crust. This differentiation would not have been possible without the interiors of the primitive planets melting as they do in high-temperature furnaces. Most planetary scientists of the 1970s thought that the process on Mars needed 1 billion years, the time required to produce enough heat from the decay of radioactive elements inside the planet. Still, looking at Martian meteorites in the 1980s revealed a much accelerated history. These meteorites lacked sufficient levels of some hydrophilic elements found in the core of Mars and showed great affinity for iron. This helped to explain why iron mostly moved from the crust of Mars to its core during the planet's accretion. The core could have formed in less than 50 million years, perhaps as little as 20 million years. Like a blast furnace, accretion produced enough heat on Mars, Earth, Venus, and other terrestrial worlds to purify the elements from the primordial mix within the planetesimals. Iron and carbon dioxide are produced from oxygen, carbon, and iron oxides in a blast furnace. Graphite from carbonaceous chondrite meteorites mixed with iron oxides generates metallic iron and carbon dioxide in a planet's magma. The molten iron gathers more heat as it falls toward the Earth's core. By contrast, refractory oxides, especially aluminum oxide and calcium oxide, rise to the top to create a layer called the primary crust. Mars's core is what size? Which elements make up its composition? The depth of Mars's core mantle border hasn't yet been directly measured. By contrasting meteorites believed to have a similar composition to planetesimals, such as the carbonaceous chondrite that fell close to Ivuna in Tanzania in 1938, with those that feature bits of Mars' crust, like the Cassini meteorite, we can learn more. About half the planet's diameter, between 1,500 and 1,900 kilometers. Mars's core is probably made of 70 to 80% iron and some nickel and sulfur. We might justify the evolutionary variations amongst the 4 terrestrial planets in several ways. The factors include starting size, the background of catastrophic cratering, and internal heat dissipation mechanisms. Mars was half the size of Venus or Earth, and almost 10 times less mass after the accretion phase, some 4.45 billion years ago. This difference would be vital for the planetary energy accumulations in several respects. Stronger impacts as accretion proceeds follow from the direct correlation between a planet's mass and the gravitational acceleration on its satellites. Moreover, radioactive element concentration increases with increasing planet size. Because their denser atmospheres prevent thermal radiation from escaping and help to retain heat, massive planets also keep heat of a better quality. This clarifies why the 2 smaller celestial bodies, Mercury and the Moon, cooled more quickly from the beginning. Mars is a transitional phase between the 2 smaller celestial bodies and the 2 bigger ones, Earth and Venus. The internal development of planets was much shaped by the random occurrence of catastrophic meteorite impacts. The Earth's mantle absorbed most elements and energy from the cataclysmic impact that created the Moon, about 4.4 mm. Or ago. Mercury, on the other hand, lost most of its mantle from another impact. Following the period of material and gravitational energy absorption, the planets emitted some of their internal heat, that is, the slow release of heat from the radioactivity of the rocks. Which procedures engaged them? A solid, stiff planet conducts heat thermally toward its surface. While heat retention is commensurate with the planet's volume, this mechanism generates heat loss commensurate with its surface area. Comparatively, a bigger planet will lose less energy than a smaller one. However, this model ignores material displacement inside the mantle, volcanic activity, or the thickness of the insulating surface layers. The heated rocks deform over geological time within the apparently solid mantle, allowing material from the depths, hot and less dense, to climb to the top where it cools. In the movement and dissipation of heat, this mechanism, called convection, is far more efficient than conduction. Whereas mantle convection has probably stopped on the Moon and Mercury, Earth boasts strong convection, almost reaching the surface at mid-oceanic ridges. Mars has a heated mantle to enable mild convection, especially under its large volcanoes where partial melting zones have generated volcanism over the past 100 million years. Unexpected detonations startled the Chassigny community in eastern France early on October 3, 1815. A stone had fallen from the heavens nearby. Appearing to come straight from a volcanic eruption, this 4-kilogram meteorite has fascinated generations of scientists. Of the tens of thousands found on Earth, about 30 meteorites of the Chassigny type fit this description. The sites of their first discoveries, Chergoti in India, Nakhla in Egypt, and Chassigny in France, directed our naming of the SNC meteorites. The Martian source of these meteorites was firmly established only in the 1980s. Their isotopic content of oxygen defines them. There are several isotopes of oxygen. Scientists have found their nucleus in Antarctica and then dated it in a lab environment. Researchers have found many Martian meteorites on the Antarctic ice, including EETA 79001. Geochemists, especially those materials that have crystallized from magma, use the radioactive decay of potassium-40 to argon-40 to determine the sources of elements. Once the rock melts, the argon from the potassium-40 decay can dissipate. The argon compacts within the rock once it has developed. Comparing argon and potassium isotopes to their starting concentrations in the Martian atmosphere helps determine the crystallization time. The age for EETA 79001 is 180 million years. It is a rather modern rock in the age of the Earth. How did researchers come to find that SNC meteorites originated on Mars? Research and dating revealed they were once part of a single, far-off parent body, sufficiently big to have produced magma and volcanism. Was Mars? Mercury? Was an old planet destroyed during solar system development? Though we have only lately been able to consider today's planets, a large asteroid impact most certainly drove the SNCs into space. The most convincing proof of a Martian origin came from the meteorite EETA 79001. Antarctica picked this up in 1980. Gas bubbles caught in dark basaltic glass specks were contained inside it. The glass developed from the major impact that detached the rock from its planet. Using in situ studies of these gaseous inclusions, the Viking landers found in 1976 that their composition matched Mars's atmosphere. As such, many researchers see SNC meteorites as real relics of the red planet and markers of its formation. Mars, Earth, and Venus have atmospheres of nitrogen, oxygen, carbon dioxide, water vapor, and trace gases, including helium, argon, neon, krypton, and xenon. The corresponding ratios of different gases and global pressures define the different atmospheres. Whereas Earth has an atmospheric pressure 90 times lower than Venus, the atmospheric pressure on the surface of Mars is between 100 and 150 times less. To ascertain the initial atmospheres of planets, planetologists must do a thorough investigation. The compositions have been much altered by the chemical and physical interactions of volatile elements, the solid crust, the liquid seas, and volcanic activity. You are quite important in this process. One can discover atmospheric components that have not changed in 4 billion years by excluding elements that define modern atmospheres from the study framework. Carbon, nitrogen, and oxygen produce carbonates and nitrates mixed into the crust. Deuterium and hydrogen could come from the breakdown of water in ice formations and oceans. The only remaining are the noble gases and their isotopes, atoms of the same chemical element with different neutron count and mass. Given their chemically inert nature, these gases are sometimes called inert gases. Measuring these rare gases, which accounted for little over 1.6% of Mars's atmosphere, the Viking probes made a noteworthy discovery in 1976. From this discovery, scientists learned much about the history and composition of Mars' atmosphere, particularly how common argon-40 is, an isotope produced when rocks break down potassium-40 radioactively, and how little neon, krypton, and xenon are. The planet's low gravity, lack of a magnetic field, and the presently uncertain history of volcanic activity further complicate the formation and history of the Martian atmosphere. These two elements help to explain why most of the primordial atmosphere vanished. Solar wind effect and meteoritic strikes. Perhaps the original water volume on Mars was higher than that of the oceans on Earth. Now we know that the process progressed with the arrival of planetesimals high in volatile elements and water, making up to 10% of their mass, during the first phase of accretion when parts of the core and mantle were formed. Studies show that half of the planet is composed of Martian meteorites. Surely a good amount of the water has disappeared. Still, some remain in the crust as ice and inside the planet's mantle. The current count is a source of debate. The solar system's planets were severely bombarded by asteroids and small celestial bodies that had not engaged in planetary accretion and were driven from their orbits by the gravitational pull of the giant planets in the first 700 million years of their formation. About 3.8 billion years ago, the peak period of this bombardment coincided with the quick and definitive migration of these massive worlds. Unlike Earth, Mars keeps traces of that event over half of its surface, mostly found in the southern hemisphere of Mars. Craters of different diameters, ranging from several meters to several hundred kilometers, abound. A body just a few hundred meters in diameter colliding with the Martian surface at 15 kilometers per second would release an energy release equivalent to several hundred megatons. The yield of the Hiroshima bomb was 13 kilotons. This impact can send chunks of the planet's surface and parts of the atmosphere into space. A deluge of trash and dust clouds may hide the residual atmosphere. Pressures several thousand times higher than those of the Earth's atmosphere and temperatures reaching several thousand degrees during the impact produce liquefaction, vitrification, and even vaporization of materials. Inside the subsurface material lie major cracks. The effect generates a compression and stress relaxation wave rapidly decompresses the rocks underfoot. This is what generates the crater. Just 1/100th of a second post-impact, the excavation phase throws debris along the crater's edge. As the material reorganizes inside the cavity, a slow process starts. A center peak or ring forms hours or days after the initial impact, comprising elements expelled from the crater upon impact, some in a molten form. The ejecta radially surround the crater. The form of impact craters varies with size. The smallest craters, less than 20 kilometers in diameter, have a bowl-shaped form, while the floors of bigger craters seem filled and could show rings or peaks at their centers. Mars is special since its topography is asymmetrical. Although their elevation is roughly 5 kilometers apart, the southern and northern hemispheres have distinct geology. Whereas the northern plains show a more modern surface with rather few craters, the high plateau of the southern hemisphere is ancient and heavily crayed. A transitional zone lies between the two sections with many buttes, single hills with steep sides and flat tops. This suggests great wear and tear on the raised plateau. The plateau's indistinct boundary fades into small buttes at about 45 degrees north. This dissymmetry has its roots in a subject of active debate and ongoing research. We are investigating two research strategies. One suggests an internal geological source, and another external one is connected with catastrophic events. Could asymmetrical convection inside the mantle cause the dissymmetry and vary the thickness of Mars's crust? Scientists could evaluate the variations in the planet's gravitational field using the changes in the paths of circling spacecraft. This information shows the crust's thickness and any subsurface anomalies brought about by mantle convection. What were the study's results? Changing the Earth's gravitational field reveals that the crust is 40 kilometers thick in the north and 70 kilometers thick in the south. Unequal convection in the mantle is not probably what causes this difference. The crust does not show the expected variations in thickness in the transitional zone spanning the plateau from the plains. Several meteoritic impacts could have weakened the northern hemisphere's crust. Studies of gravitational anomalies and subsurface-sounding radars expose thick layers of silt covering impact sites. Nowadays, sediments hide the cratered surface that developed concurrently with the southern plateau. Then, several kilometers of strong material deposits from the erosion of the crater-filled high plateau covered it. We do not fully understand why the northern hemisphere first experienced the most important effects. The first spacecraft to fly to Mars at very low altitudes was Mars Global Surveyor, MGS, in 1997. Studying the magnetic field of the ionosphere, the atmospheric layer ionized by UV light and solar wind, was one of its mission goals. When MGS arrived at Mars, the magnetometer went active. As expected, the magnetic field peaked as the probe passed the ionosphere. Yet to everyone's surprise, values peaked once more during some low passes across the most ancient surfaces of the planet. Previously thought to be lacking such a field, MGS found the relics of an ancient and once strong magnetic field able to magnetize the surface. Nowadays, planetologists are asked about the source of this discipline and the causes of its disappearance. On Earth, movements within the iron core, fluid and a strong conductor of electricity, create magnetic fields. We do not fully understand the exact mechanism of producing such fields. An electric current is produced in the liquid core by convection, defined by the ascent of hot iron from the center to the mantle border for cooling and consequent descent. This creates a magnetic field via the dynamo action. From where comes electric current? Randomly produced micromagnetic fields within this medium seem to generate electric current, producing a global magnetic field. Mars had a sufficiently heated liquid core to enable convection and generate a magnetic field after the accretion phase some 4.45 billion years ago. The core most likely cooled quickly, and several 100 million years later, at most 500 million, the remaining heat was insufficient to start convection. Then conduction started, and the Martian dynamo engaged when convection stopped. Today, Mars's crust bears residual magnetic memory from the active dynamo. Scientists can only approximate when the dynamo stopped running by dating objects from the cratered southern terrain. Two small natural satellites move in opposite directions in the Martian atmosphere. With small dimensions and twice-daily ascension in the west, Phobos, the larger of the two. Every 5.5 days, Deimos rises on the eastern horizon. From the surface of Mars, their apparent diameters are roughly 3 times and 17 times smaller than those of the Moon, as seen from Earth. Soviet probe Phobos 2 photographed Phobos as it approached Mars in 1989. Prematurely lost, the Phobos 2 probe sought to closely study this satellite. The operation involved placing a module on Phobos, which can transition in phases due to its reduced gravitational force. Under the Phobos Grunt new mission, the Russian Space Agency plans to send samples from Phobos back to Earth within the next 10 years. Given the Sun's apparent diameter, 2/3 that of Earth, only partial solar eclipses, previously observed on Phobos, can occur on Mars. Phobos and Deimos's dimensions and arrangements point to them being asteroids, a theory consistent with their rather low densities about the Moon or Mars. Phobos has a density almost twice that of water. Deimos has 1.7, the Moon has 3.34, and Mars shows a density of 3.9. About 95% of the sunlight the satellites receive is absorbed by their surfaces. They have this feature with particular asteroids orbiting the Sun between Mars and Jupiter at distances between 3 and 3.5 times that of Earth from the Sun, 450 to 525 million kilometers. Should Phobos and Deimos be indeed asteroids, we can conjecture their arrival time and mechanism. Mars must have acquired them, just as certain satellites Jupiter, Saturn, and Neptune have done. Still, this does not produce a solution. An asteroid must be slowed down for capture. Space probes must turn on their engines to produce a braking effect and reach orbit. Various models are under review. Inspired by the story of the Earth and its moon, the first theory holds that a celestial body crashed into the planet, throwing trash into orbit and then reaccreted. Unfortunately, Phobos and Deimos have low density, so this approach is unlikely. Another model uses aerobraking, in which the body rapidly decelerates across a thick atmosphere. Mars had an atmosphere at formation, but solar activity quickly disappeared. Should this model fairly depict reality, Phobos and Deimos could be the last traces of the planetesimals that helped Mars to form some 4.5 to 4.3 billion years ago. The question is still open. Is it conceivable that somewhere an oasis existed where life could have flourished? Our story moves in a world very different from the one we now live in. Its geological record reveals events from a young planet, sometimes under the influence of multiple celestial bodies still in orbit around the Sun. Temperatures on this young Mars allow liquid water. Rivers and lakes erode the surface to collect silt. Some 3.8 billion years ago, the first microorganisms began and developed on Earth, where environmental conditions were only somewhat more favorable than those on Mars. Could it be that life started on the Red Planet? Mariner 9 made an amazing discovery. 1972 about unusual valleys like desiccated riverbeds. Soon after, researchers found similar fluvial features around the 3.8 billion-year-old southern hemisphere cratered plateau. More modern landscapes, however, lacked evidence of these valleys. Mars showed conditions fit for the formation of river valleys some 3 billion years ago, conditions not seen since. Were we actually seeing proof of rivers? This documentary series investigates several flow properties generated by liquid water. As detailed in this section, many dendritic fluvial valleys, including meandering examples like Nirgal, Nanedi, and Ma'adim, were formed over 3.5 billion years, presumably during milder temperatures than the present. There is a notable outflow. These channels span more than 100 kilometers and are fresh. Presumably violent catastrophic discharges created these channels at several points over Mars's history. The temperature may not have deviated much from present records. Small traces of gullies spanning several hundred meters seem to date from a few 100,000 years ago or perhaps more recently. Yesterday, in geological terms. Some of these valleys, which stretch up to 1,000 kilometers, have several branches with tributaries gathering like a drainage basin. This rather tree-like arrangement suggests that the liquid flowed long during the episode. Although other theories involving lava and liquid carbon dioxide have been put forth, Planetologists agree that water was the liquid responsible for forming the valleys. Given the Martian network's age and certain features' gradual loss over time, it is difficult to match the valley networks on Mars to those more recent on Earth. Scientists at first thought that Mars had less branches than Earth. New thermal imaging, however, has discovered many hitherto invisible tributaries in systems with Earth-like densities. Many questions develop. Is a warm and humid environment necessary to start such flows? Could a cold Arctic environment have caused a comparable result? Can we clarify our observations by including the water cycle, precipitation flowing over or into the ground? Whatever the conditions, the surface water must have been in a stable liquid form to erode such valleys, implying that at least intermittently, the atmosphere during that period was denser than it is now. On Mars, ancient valley networks could resemble similar landforms on Earth. Still, there are differences. Still, questions are up for debate today about the need to call for floods and terrestrial-type precipitation in the past of Mars. Some Martian river valleys could have started from. As the Bakhuizen crater shown in the above picture shows, a particular number of branching valleys result from the slopes of volcanoes or impact craters. One theory is that rising magma causes subsurface water near a volcano, or, after an impact, to become heated, creating a convection cell, hydrothermal circulation. Rising to the surface, heated water forms springs and supplies rivers. Lava can build up in circular fractures, vaporizing below ground water and producing geysers and hot springs. A long, sharply incised, winding, branching valley sits on the cratered southern plateau. Examples include Nanedi Valles, Ma'adim Valles, and Nergal Valles. Unlike the earlier defined networks, these features have few tributaries. Surface water runoff is proposed as a contributing factor, yet it does not adequately explain the valley excavation's considerable depth, several hundred meters. Another theory holds that rather than surface water movement, subterranean water flows cause the valley's flanks, sometimes called sap, to erode. Experts are finding that precipitation, rain or snow, has greatly contributed to the great erosion seen in the planet's most ancient landscapes, at least intermittently. Precipitation was probably necessary in the past to replenish ancient subterranean water reservoirs in places where the shape points to their presence. Mars features many impact craters that might have once housed lakes. In an environment fit for liquid water roughly 3.8 billion years ago, the bowl-shaped craters could have helped water bodies grow and facilitated sediment deposition. For a very long time, this was only a theory. Mars Global Surveyor images from 1999 clearly showed such characteristics. Usually found in their core areas, the floors of some craters had highly stratified dark and light layers. Lakes on Earth often correlate with this kind of sedimentary deposition. Scientists have found evidence of lakes that once existed on Mars. The delta-like formations seen in some deposits close to Martian craters could be explained by the sediments found in these craters having been deposited in lakes fed by rivers, usually showing that rivers are active and that water could enter the crater. One or more channels run around the margins of the craters. The dating method based on small craters confirms that these deposits are ancient, almost contemporaneous, with the river valley systems of the southern high plateau. In other cases, erosion, a phenomenon also seen on Earth, though to a smaller degree, has exposed sediments that have been entombed for long periods. Though much convergent evidence points to the sediments from lakes, it is not always clear-cut. Sometimes one imagines a deposition situation that is free of water. The strata might start from volcanic activity, which produces ash deposition. Maybe winds carried dust to these places. According to the latter theory, the sediments are stratified dunes with cyclical variation in deposition, depending on climate changes. Given that Mars has suffered wind erosion over the past 3 billion years, This idea is more realistic than it first seems. Over what length of time could the winds have generated what formations? Nothing on Earth can offer a similar experience. Salts and clay provide a fresh understanding of Mars's moist past inside some strata. Liquid water has powers beyond only shaping river channels and shifting silt. Like on Earth, the chemical composition of Martian rocks could have changed. The best approach for research would be to do laboratory mineralogical analyses of these rocks. Yet it is not now practical. Nonetheless, by matching the spectral characteristics of rocks, such as their coloration, with those of terrestrial samples, we can remotely study the composition of Martian minerals. The TES spectrometer on Mars Global Surveyor found a distinctive mineral, crystalline hematite, in 1998. This is an iron oxide that usually requires liquid water for growth. On Mars, hematite has been found in ancient sedimentary regions, including Terra Meridiani, south of Arabia Terra. Was there a lake there, perhaps? Seen in false color, this is an outcrop of sedimentary rocks close to the Opportunity landing site in Terra Meridiani. Mostly composed of sulfated salts layered in fine strata, the rock most likely originated in liquid water. It shows minute mineral spheres, blue, with diameters expressed in millimeters. As the wind chips away the rock, some have dropped and covered the ground. To clarify this question, Opportunity, a NASA rover fitted with scientific tools, conducted an in-situ study at Terra Meridiani. On January 25, 2004, Opportunity arrived at a small crater 22 meters in diameter. This lucky chance let the lander's camera find stratified, light-hued rock formations on the crater walls. Examining these rocks, the Opportunity rover found hematite. Like berries in a muffin, it showed up as millimeter-sized, spherical grains, called blueberries, buried in the bedrock. The presence and configuration of centimeter-scale layers apparently preserved the imprints of waves in shallow water, suggesting deposition by liquid water. Opportunity's equipment revealed that the rock mostly consisted of hydrated sulfate salts. On Earth, especially when evaporation increases the concentration of dissolved minerals, such deposits grow close to the bottoms of shallow lakes. Geologists thought this part of Terra Meridiani had a similar past. Opportunity studied the rocks at the Terra Meridiani site, while the Mars Express orbiter used its OMEGA camera to thoroughly map Martian mineralogy. This new device is a clever fusion of an imaging tool and a spectroscope. Several sites with rather high sulfate salt concentrations were found. Towards the northeast of Oporto City, a large area spanning hundreds of kilometers has been found, where sulfates are present on particular slopes making up most of the surface. Mostly sulfates, many sedimentary layers on Valles Marineris' floor and walls point to liquid water having some influence in their creation. Still, the story continues. Omega also found clays, suggesting a different age when liquid water passed through another habitat. Though only in the distant past, the first 700 million years of planet Mars' existence, it most certainly had several phases marked by different availability of liquid water. The general view is difficult to rebuild, since time has blinded our clarity, and every event has mostly destroyed the traces of its precursor. The rover Spirit landed firmly on the floor of the vast Gusev crater on January 4, 2004. We sent the rover to this site based on our theory of a lake inside this crater. Gusev is situated at the end of Mardim Vallis, a 900-kilometer-long valley across the raised southern plateau. Mardim Vallis begins at a spillway in the divide of a sizable drainage basin based on surface area measurements of the land. Large sedimentary deposits abound in the Gusev crater, which also gets plenty of water flow. First disappointed were planetologists, who had great hopes for Spirit's discoveries. It found very little over its 3-kilometer path. mostly basaltic volcanic rocks over 5 months. The lava flows have hidden all sedimentary deposits from any lake in this area. Historically, the water contained rather old, stratified rocks. The hill represents an island tucked within the lava flow. Hematite was present, along with many hydrated minerals, including sulfate salts and goethite, and oxidized iron minerals requiring water for their formation. Scientists kept arguing about whether Ma'adim Valles was connected with this water modification. Could it come from a far more ancient period, of which little evidence exists? Particularly in certain regions, the Omega mapping spectrometer on Mars Express found 2 types of Martian rocks suggestive of formation resulting from liquid water, sulfates and clays. These clays were found in ancient settings, particularly where meteorite impacts or wind erosion had exposed long-buried deposits. Early Mars's history saw liquid water seeping into the ground for long enough times to allow clay to develop. Sulfated salts, thus, were more likely to develop in a drier and more acidic environment. A controversial theory holds that a body of water was once called Mars' Northern Hemisphere home. After the massive meteoritic bombardment 3.8 billion years ago, the topmost kilometer of the Martian subsurface most certainly had a volume of water, equivalent to a worldwide ocean 500 meters in depth. The evidence of ancient rivers and lakes on the southern high plateau suggests that volcanic and hydrothermal activity and climate could support a surface water cycle here. Under these conditions, significant water and sediments must have migrated into lower-lying regions, especially onto the northern plains. As such, a large swath of liquid water or mud could have periodically existed in a region known as Oceanus Borealis, 4 times the size of the Arctic Ocean. Hellas Planitia might have been a real inland sea during that time, while the impact basin Argyre could have connected with the northern plains. Once created, evaporation and subsoil intrusion caused this ocean to progressively disappear. The temperature changed to glacial, burying some water below ground as ice. Some planetologists speculate that oceans have developed and reassembled cyclically throughout the first few billion years of Mars's early history. Do any traces of this once existing ocean exist? Molar laser altimeter data from the Mars Global Surveyor confirmed the Northern Ocean theory. Molar revealed that elevations stayed rather constant over 1,000 kilometers in places along historical shorelines. This helps explain the presence of an ocean since shorelines form topographical ledges. Still unresolved, though, is this one. Given Mars's carbon dioxide atmosphere, why did the water not absorb carbon dioxide to generate carbonates like chalk? No such rocks have been found on Mars by planetary missions. Assuming the oceans existed, were they too acidic for such processes? Though the moderate temperature of Mars remains a mystery, which holds true even with a young and dimmer sun, planetologists argue passionately about how ancient lakes and river valleys formed. The general agreement is that although intermittently, a slow erosion process by flowing water requires rather warm and humid surroundings. There is a remarkable presence of such a temperature for 2 reasons. Although Mars is rather far from the Sun, experts believe that the young Sun was 25% less brilliant than it is now during the pertinent time. Under these conditions, the world's theoretical average temperature would increase, adding to the mystery of Mars's climate. What conditions prevailed on Mars 3.5 to 4 billion years ago? Apart from other less stable gases, the greenhouse effect of carbon dioxide and water vapor heated the primordial Martian climate by CO2 ice clouds, reflecting thermal radiation back to the surface. Acting as a reflecting survival blanket, such clouds would have greatly limited the planet's cooling capacity. Mars's recently developed and hence heated interior produced a geothermal heat flow 5 to 10 times stronger than what is now recorded. This helped the subsurface to be heated and maintained a hydrothermal system, crucial in determining the Martian temperature. In the end, the catastrophic events of Mars's early history could have occasionally produced the warming of some areas. Erosion is slow, but historically it has been rather more severe. One of the oldest areas on Mars, Noachis Terra, is shown here as eroded for almost 3.8 billion years. The expanse shown here spans 900 kilometers in width. The picture shows the presence of ancient fluvial valleys, and careful study reveals that most minor craters, less than 15 kilometers in diameter, have been erased, while most major craters have seen notable erosion. Craters show better resistance against erosive pressures in places with the least recent surfaces. These records show that erosion happened thousands of times more intensely in the distant past. Solar radiation heats a planet, while infrared radiation emissions into space cool it. The greenhouse effect results when cooler atmospheric gases let sunlight pass through them. By absorbing and storing the surface's infrared thermal radiation, these gases help the planet not cool. The primordial Martian atmosphere consisted mostly of carbon dioxide with minor nitrogen, argon, and water vapor components. Enough CO2 would have been present during that time to maintain an atmospheric pressure of roughly 1 bar, like Earth. Only CO2 and water vapor can help create the greenhouse effect in such an environment. Studies indicate that these two gases cannot produce temperatures higher than 0 degrees Celsius. Dealing with this problem requires considering other greenhouse gases, including sulfur dioxide, methane, and ammonia. This mix seems unlikely since these gases would have been chemically unstable in a primordial Martian environment except from constant generation by volcanic activity. The warming of Mars most likely results from clouds of carbon dioxide ice. We expect a thick atmosphere, rich in CO2, which will tend to gather into clouds of CO2 ice. Refer to the diagram on page 68 to see how these clouds might reflect and effectively store thermal energy released from the surface, greatly warming the atmosphere, underneath which rivers flowed in continuous darkness. We can see a lush Mars surrounded by thick clouds. To justify such a situation, we need much more data. Life began on Earth some 4 billion years ago. What about Mars? That raises interesting questions for the scientific community. Might life also have started on the red planet? Suppose that life on Earth was not the only manifestation of life in our solar system. About 3.5 billion years old, Earth's first known sedimentary layers show signs of life activity. What elements helped life to start on Earth early on? Nobody's knowledgeable. The discrepancy between inanimate chemical elements and the most basic known life forms cannot be reconciled. Moreover, the rocks offer no strong evidence of such a change. All theories agree that liquid water is vital, and that complicated organic molecules arrived on Earth from meteorites and comets, which struck the planet in great numbers then. Energy and nutrients provided by volcanism and hydrothermal activity have greatly helped. Similar circumstances also applied on Mars. There is no a priori justification for excluding the possibility of life emerging on Mars 3.5 to 4 billion years ago, if basic and recurrent physicochemical processes define life on Earth. Studies of Mars reveal that surface conditions allowed liquid water a limited lifetime, at most several 100 million years. Any life form that might have evolved there would have been only primitive. Following over 2 billion years of unicellular progenitors, multicellular species emerged on Earth, including the first animals and plants. Was this the result of Earth's physical and chemical conditions, such as oxygen levels unfit for the presence of more advanced organisms? Or was it due to the long period needed for necessary genetic evolution? Events on Mars might have happened differently, and some hopeful scientists have hypothesized that more evolved life forms coexisted simultaneously. Mars, being smaller than Earth, most certainly cooled far faster. Moreover, it did not experience the major influence that produced our moon and deprived the Earth of its primordial atmosphere some 4.5 billion years ago. Life may have started on Mars before it arrived on Earth. Mars suffered multiple meteoritic collisions during its forming years. These regularly ejected bits of the surface of the planet into space. Many have affected Earth, and maybe still do. Within these pieces, conditions could allow many spores to survive. A convincing theory holds that Martian species might have seeded Earth from interplanetary space 4 billion years ago. How might we find traces of life that disappeared billions of years ago? This is a scientific curiosity question, and a vital search that might change our perspective of the universe and our position. One of the most important philosophical and scientific turning points in human history would be the knowledge that life formerly flourished on Mars. Just showing its absence would be interesting as we consider why life evolved on one planet rather than the other. Given that both show similar conditions, Mars provides a better research environment than Earth, where events from more than 3 billion years ago have destroyed evidence. One could find a hint to the missing link between inanimate and biological matter on the red planet. Which criteria ought we to give importance? Post-mortem, living cells usually break down quickly and lose their shape completely. Still, mineral fossilization has often helped to reconstruct the forms, appearances, and organization of many ancient microorganisms. Under this process, silicates in water gradually stick to organic molecules in cells. This creates a solid mineral layer capable of preserving fine characteristics, including bacterial membrane roughness. On Mars, too, a similar process could have happened. Should any living entity ever evolve there, we could finally find traces of its form. From where should we start the search? Many scientists ask, as we create missions to bring samples back to Earth. Preferred sites are sedimentary basins, where water might have accumulated. Holden Crater, AB, lies 1,000 kilometers north of the Argyre Basin. Ancient lake sites are especially interesting, since any Martian life present may have survived in a stable habitat following the average temperature of the site dropped below 0 degrees Celsius due to a significant layer of permanent ice. The Antarctic dry valleys, sea, amply highlight these sites. NASA experts have conducted many studies on them. These Antarctic lakes have an unexpected richness of ecological niches, D. Bacterial colonies spanning several tens of kilometers blanket their depths, notwithstanding the lack of precipitation and sub-zero temperatures, except a few days annually. Another avenue of research is the search for traces of biological matter. Unfortunately, the Viking landers found that Martian soil is chemically quite aggressive, full of oxidizing compounds that destroyed all organic molecules in the uppermost few meters of its surface. Determining the mineral or biological source of such molecules found at deeper depths is difficult. Based on current studies on Earth, the most complicated molecules linked to living entities should have vanished entirely on Mars 3.5 billion years ago. Still, the constantly frozen ground can preserve some very strong compounds. Any life that once existed on Mars could have concentrated particular chemical components at ratios that are difficult to explain using non-biological mechanisms. On Earth, living cells contain rather large concentrations of pyrite, magnetite, and phosphates. As markers, all living things on Earth preferably use carbon-12 over carbon-13, a chemically similar but heavier isotope. Like Earth, Mars could also see this event. With dates ranging from 180 million to 1,400 million years, most SNC meteorites from Mars are essentially modern basaltic rocks. One exception is ALH 84001, found in Antarctica's Allen Hills, thus the acronym, 1984. About 4 billion years ago, this rock began in a temperate, chemically reducing environment quite different from the oxidizing conditions found on Mars today. About 3.6 billion years ago, ALH 84001 showed fissures suggestive of water movement, which caused notable carbonate nodules to deposit. Their diameters run about 1/10 of a millimeter. Organic chemicals abound in this meteorite. It is a singular and priceless monument to Mars's time as an oasis. Once discovered in 1993, this unusual meteorite attracted attention worldwide. In 1996, a group of American scientists under David McKay of NASA proposed that ALH 84001 might contain evidence of extraterrestrial microbial life. Where, then, was the evidence? This is the remarkable story of a Martian-originating meteorite. Isotopic dating has produced the chronology of this meteorite. This process examines the ages of elements in the rock that developed during crystallization. 4.5 billion years for volcanic rock and 3.6 billion years for carbonates. The heat events following impact, 4 billion years, and its cosmic ray exposure throughout space. According to analysis, cosmic rays started the synthesis of fresh isotopes 16 million years ago. The process stopped suddenly 13,000 years ago. We looked at meteorite ALH 84001. When discovered, the object was covered by a fusion crust, usually found in meteorites heated by friction as they pass through the Earth's atmosphere. ALH 84001 displayed many fractures and cavities when bisected. Unusual spherical carbonate inclusions measuring 100 to 200 micrometers, 0.1 to 0.2 millimeters, in diameter were seen under the microscope. Less than 0.5% of the whole consists of these entities. D. Scanning electron microscope view of a carbonate surface. Small stick-like structures generated by a sequence of claimed fossils measuring less than. First, there were complicated organic molecules known as polycyclic aromatic hydrocarbons, PAHs, which might have derived from microbial breakdown. Second, the carbonate nodules' form and chemical composition matched those of some land bacteria, displaying many layers of iron oxides, particularly magnetite. Under the electron microscope, fossils, less than 1 millimeter and looking like microorganisms, were finally visible. Many scientists have questioned McKay's conclusions over the years. Could surface modification and abrasion during observation produce the microfossils? Is it possible to ascribe the PAH's carbonate nodules and magnetite deposits to natural processes? Ultimately, it was discovered that the very ancient carbonate deposits originated from space. However, given the meteorite under Antarctic ice for 13,000 years, some organic components most certainly mixed in. Although ALH 84001 may not prove that life once existed on Mars, it indicates that Mars had mild and most likely wet conditions in its early years that would have let organic molecules survive without rapidly disintegrating. What elements stopped Mars from veering in the direction of Earth? Mars once had an Earth-like, temperate, moist climate. It is cold and dry with a thin atmosphere that makes rivers impossible. Scholars agree that losing most of Mars's atmosphere marked a turning point in its fate. Under what conditions did this happen? Mars and Earth collided with asteroids several kilometers in size during the first billion years of their existence. And these strong impacts could have sent a lot of Mars's primordial atmosphere into space. The Earth's stronger gravitational pull helped it retain its gases more successfully. The loss by impact theory does not help to clarify the causes of Mars's present low atmosphere. Calculations of atmospheric erosion indicate that the Martian atmosphere was noticeably denser following the intense bombardment period. Atmospheric carbon dioxide chemically combines with surface rocks in liquid water to create carbonates, reducing air volume. On Earth, tectonics constantly recycles rocks to preserve equilibrium in this process. Once carbonates are buried deep within the Earth, volcanoes spew carbon dioxide into the atmosphere. Most of Mars' atmosphere would have turned carbonates without plate tectonics. The question that then arises is, where are these carbonates Conclusive proof of their existence has not yet come from even the Omega mapping spectrometer on Mars Express, which can detect low levels. The Martian meteorite ALH 84001 revealed few traces. Does the Martian environment completely destroy any traces of carbonates on the surface of the planet? One can imagine a situation whereby carbonates never developed. Surface water would have been rather acidic if Mars's primordial environment encouraged sulfate deposition, preventing the development of most carbonate forms. A planet must have enough gravity to preserve its atmosphere. For example, the simple thermal motion of a gas molecule suffices to enable its escape into space on a quite small body like the Moon. Still, except for the lightest gases, hydrogen and helium, this loss is negligible on Earth. What is Mars's present situation? The red planet has enough mass to preserve significant water vapor and carbon dioxide concentrations. More processes, however, produce the ejection of atoms and molecules. Contributors are reactions brought about by solar UV radiation and the interaction of the solar wind with high-altitude ions. Beyond the atmospheric boundary, the Earth's magnetic field deflects the solar wind. For millennia, Mars lacked a magnetic field. Thus, the solar wind's magnetic field greatly accelerates oxygen ions in its upper atmosphere by colliding with CO2 molecules and ejecting them into space. Do hidden carbonates exist on Mars? The Martian subsurface could have theoretically absorbed some of the old Martian atmosphere as carbonates. The surface lacks these carbonates. Still, several examples of ancient rivers, e.g. Hebrews, valleys, seem to have sculpted their beds both at the surface and subsurface by dissolving rocks to produce a karstic hollow. This form resembles Earth's limestone areas, which abound in carbonates. Does the subsurface material in this region consist of a layer of carbonates presently hidden under dust? Could early life forms have survived in such a hostile environment? The Viking probes set out to hunt life on Mars's surface. In 1976, one of the main objectives of the Viking probes was to identify life on the Martian surface. Designed for excavation, an articulated arm gathers Martian soil samples. We examined the samples, including labeled release trials, gas exchange, and pyrolytic release. Mars is right now cold and dry. Its surface suffers great UV radiation without a protective ozone layer, which would be fatal for most living entities, especially those like those on Earth. Strong oxidizing agents in the surroundings seem to have cleaned the top layers of soil of germs, like the water with added oxygen used to kill bacteria. If life started on Mars under these conditions, how could it have survived to this day? Regarding this, even the most optimistic analysts exercise caution. Our planet's research has shown that some microorganisms can survive under the most difficult conditions. They still flourish under very strong pressures, temperatures above 100 degrees Celsius, highly acidic or alkaline conditions, or depending on hydrogen sulfide or iron for survival. Many kilometers below the surface of the Earth, in basaltic rock in Oregon, researchers discovered species with an iron-based metabolism in 1995. Every kind of life depends on liquid water. Should life continue on Mars, we must look for it in crevices, where liquid water still resides. Many kilometers below the surface is a possible site where the geothermal heat of the planet keeps temperatures above 0 degrees Celsius. Like in Oregon, interstitial water could support life. Proximal to the surface, Martian volcanism probably creates warmer areas even if they are declining. Like Earth, life could take advantage of the more plentiful chemical resources found in such places. Like subglacial Lake Vostok in Antarctica, one could see liquid water bodies forming under Mars's permanent polar caps. The Viking probes probed the Martian surface. To determine whether Martian life can use photosynthesis to absorb carbon dioxide, the pyrolytic release experiment was designed. None of that sort of thing was found by us. Microbes that have broken down organic compounds into their component gases were the target of the gas exchange experiment. Even after the sample was sterilized at 145 degrees Celsius, a considerable amount of oxygen was still produced, suggesting chemical oxidation. Rather than suggesting the existence of life, the experiment showed that the surface of Mars is an oxidizing and sterilizing environment, similar to a medical disinfectant. We designed the label release experiment to detect the radioactive labeling of organic matter's conversion to carbon dioxide. The experiment was successful because, as predicted, when bacteria were present, the sample experienced a change that stopped suddenly when heated. Since the alternate apparatus, a gas chromatograph coupled with a mass spectrometer, can detect trace levels of organic compounds, the decision was ultimately disheartening. Everyone was taken aback by this. According to previous research, the labeled release experiment demonstrated the operation of inorganic processes in an oxygen-rich environment. However, not all experts hold this view. Oxidation and ultraviolet light have wiped out any trace of organic matter on Mars' surface. While the idea of Martian life requiring a stable environment within its bionishes seems implausible in light of the planet's evolution over billions of years, who knows what surprises the future may hold regarding this topic? Mars has been shaped over billions of years by a combination of lava, ice, and intermittently flowing water, creating the Martian landscape we see today. However, our understanding of this history is limited, with what little we know refined by geologists in light of new discoveries. Unexpected revelations and challenging questions are part of what every space mission brings. At its early stage, Mars was a very active planet. Its gigantic volcanoes show that it was once hot enough to support widespread volcanism. The primordial and present atmosphere and water may have come from the mantle as volcanic gases. But this violent eruptive phase quickly set in motion a process that slowly dissipated internal heat by convection. This document outlines the history of Mars's mantle and its magnetic field. Between 4.4 and 4.0 billion years ago, vigorous convection currents transpired in Mars's mantle. Refer to diagram Mantle Epoch 1, resulting in surface renewal, a notion that remains unverified. The loss of heat by convection from the mantle induced convection within the iron core, resulting in movements that generated a magnetic field, core Epoch A. After several 100 million years, convection diminished, and the crust stabilized at the surface. The planet entered its single-plate tectonic phase, Epoch LLA. The convection diminished in intensity, leaving only a few hot spots, Epoch LLB. In the core, convection transitioned to conduction as the heat dissipation mechanism, resulting in cooling. The movement within the core and the resultant magnetic field ceased, Epoch B. Cooling will persist, and convection will cease in the mantle, Epoch All, solidifying a portion of the core, Epoch C. Mars will subsequently remain tectonically inactive. Mars's internal heat was first generated by accretion and forming an iron core. Later, it was maintained by the radioactivity of uranium, thorium, and potassium in the mantle. The planet will cool in space after all the energy from formation and radiation dissipates as heat. Convective currents in the mantle transfer this internal heat to the surface. Just like water moves from a saucepan to a saucepan, the solid Martian mantle changes shape and shifts, bringing warmer material from deeper into contact with the cooler layer closer to the surface. However, convection is limited to the area between the core and several hundred kilometers below the surface. Convection in the mantle cools the crust. Mantle convection occurred vigorously during the initial 2 billion years of Mars's history. Disintegration or ascent into the crust in lavas progressively eliminated the most radioactive elements from the mantle. However, convection did not completely terminate. Some models suggest that the slight convection decrease on Mars is caused by its crust, which is now filled with radioactive materials, acting as a heat barrier over the mantle. The continental crust accounts for 30 to 40% of Earth's heat production. The increasingly dense carapace of Mars has encased its mantle within a stiff and insulating layer referred to as the lithosphere. The depth ranges from 500 kilometers in the south to 150 to 250 kilometers in the north. Mars has replicated the Moon, which possesses a lithosphere 800 kilometers thick and retains its liquid core. The red planet likely possesses a heated mantle and a molten core, with some scientists suggesting that the mantle may be partially molten beneath some volcanoes due to the insulating effect of the crust, where recent lava flows have been detected by Mars Express. Mars is characterized by its many gigantic volcanoes, some so large that they reflect recent geological activity. The most powerful volcanoes on the planet are located in the Tharsis and Elysium regions. They have a history of releasing large amounts of gases like CO2, SO2, and water vapor, which probably caused global warming and sulfate deposition. The Tharsis region is characterized by a much elevated bulge, 5,000 kilometers in diameter and 5 kilometers in height, atop 4 massive extinct volcanoes: Martian Mons, Valles Mons, Ascraeus Mons, and Olympus Mons. These formations are morphologically similar to the Hawaiian shield volcanoes, with gentle inclines, not exceeding 6 degrees, and collapsed areas, calderas, at their peaks. They are formed by accumulating highly fluid lava flows, emphasizing their broad bases and gradual inclines. These pie-shaped volcanic formations may span hundreds of kilometers in width. They predate the shield volcanoes of Tharsis. They are located near Tharsis, e.g. Apollinaris Patera, and within Elysium, Hadriaca Patera, Tyrrhena Patera, and Amphitrite Patera. Their structure includes a central caldera and lava flow canals along the flanks. Alba Patera, north of Tharsis, and Apollinaris Patera have had explosive hydrothermal events, driven by interactions between their magma chambers and subterranean water. The resultant explosions were marked by the expulsion of pyroclastic material and dense ash clouds referred to as nuis ardentes. It is believed that these ash deposits, known as ignimbrites, were subsequently eroded, resulting in troughs extending several kilometers that were carved. These are a separate group of volcanoes, mostly found in the Tharsis area, close to the shield volcanoes. They are smaller than the shield volcanoes, and their sharp inclines, about 8 degrees, may be due to a thicker lava. Some of these volcanoes may have had an explosive phase after the fact. Olympus Mons is a giant. Its volume is 50 to 100 times bigger than the greatest terrestrial volcanoes. What is the process of its formation? It is just an aggregation of lava flows from a subterranean magma reservoir. On Earth, this type of volcano is called Hawaiian, named after those found in the Hawaiian Islands, which rise over 7,000 meters above the ocean floor. The magma chamber of the colossal Olympus is at least 3 times larger than that of a Hawaiian volcano. Nonetheless, the explanation for its immense size lies not in its formation, but in the duration of its development. Plate tectonic processes on Earth displace the crust above the magma chamber as lava flows, resulting in smaller volcanoes such as those found in the Hawaiian Islands, rather than a single huge volcano. The 6-degree slopes of Olympus Mons give it some Hawaiian characteristics, but it also shows features typical of Icelandic volcanoes. For example, an escarpment 6,000 meters high surrounds the volcano's base, which was likely formed by the distortion of lava and ash layers, by the massive mass of the volcano. 6 overlapping calderas form the 80-kilometer diameter and 2,600-meter-deep caldera of Olympus Mons. The large bulk of the volcanic dome causes slumping, which shows up as fissures, see photo on page 95. To the northwest of Olympus Mons, extensive aureoles reach up to 700 kilometers. Their source is unknown. Erosion of volcanic deposits or extensive fracturing could be their causes. Another theory suggests that ancient glaciers may have been involved. Based on crater counts, the peak caldera was formed between 100 and 200 million years ago, with the last lava flows on the volcano's slopes being about 2 million years old. The HRSC camera on the European Mars Express spacecraft has greatly improved the timing predictions for the most recent volcanic activity on Olympus Mons, which could still be active. Mars's volcanism can create impressive features like Olympus Mons. The viscosity of lava determines many other characteristics. Evidence of recent lava flows stretches hundreds of kilometers from the flanks of most Martian volcanoes, including Tharsis, Elysium, Hellas Planitia, and Syrtis Major. These flows resembled those of Hawaii's shield volcanoes, but their volume may have been 5 times larger. Due to Mars's absence of plate tectonic activity, reduced gravity, and low atmospheric pressure, much larger quantities of gas, lava, and ash were expelled. The origins of the vast lava sheets that cover plains like Utopia, Acidalia, and Lunae Planum remain a mystery. Faults and fissures are considered how this prominently flowing lava has ascended. This type of volcanism is similar to that of the Lunar Maria, with the main difference being that the Moon's volcanic activity ended 3 billion years ago, while Mars lava flowed relatively recently. Natural features along the slopes show that successive deposits have accumulated to a depth of several kilometers. Since the end of the meteoritic bombardment 3.8 billion years ago, more than 60 million cubic kilometers of lava have been spread across the Martian plains, with an average of 0.016 cubic kilometers per year. The total volume of the volcanic deposits, including volcanoes, is equal to the following. Mars had an active geology until very recently, as the gigantic volcanoes of Tharsis show. Volcanism and substantial surface alteration are products of intense mantle convection currents that interact with the crust, with some surface deformations appearing as crustal extensions or expansions, and others as compressive features. A fascinating feature of Tharsis is the thickening and elevation of the crust in this area, caused by subsurface converging convection currents. Faults in this region are arranged in a radial array, with collapsed troughs, graben, often seen between the faults. Ridges organized concentrically around the bulge's core are compressive structures. The ridges on Lunae Planum are similar to those on the Lunar Maria, long linear landforms with a mean width of 5 kilometers and a maximum elevation of about 300 meters. Presumably formed by surface compression, the crust secures these wrinkled or compressive ridges to depths of many kilometers, where the presence of volatile substances, such as water and hydrous or carbonic ice, has surely allowed one layer to slide over another. Ridges like these may be evidence of the contraction of the Martian crust during its cooling period. Mars's extreme topography is one of its most striking features. The planet is home to the largest canyon in our solar system, Valles Marineris, which stretches eastward from the Tharsis volcanoes and forms nearly parallel to the equator. The canyon is 3,500 kilometers in length, 300 kilometers in width, and 7,000 meters deep. This extension formed a network of parallel faults within a complex arrangement of collapsed trenches. Some planetary scientists see the Valles Marineris complex as a much larger version of the East African Rift Valley. On Mars, the plateau has sunk to 7,000 meters, and the crust has stretched enough to let magma rise into the faults, which have receded, causing localized surface collapse. As a result, depressions resembling lines of adjacent craters have formed along collapsed trenches. The chasms of Valles Marineris have been widened by landslides. In the central region, at a depth of 5,000 meters, the canyon widens to form long depressions called chasmata. These features have steep inclines and sometimes show floor deposits that have collapsed and spread over as long as 200 kilometers. The size of these fans has led experts to estimate that the landslides that formed them moved at about 300 kilometers per hour. The canyon floors show substantial stratified deposits in several places. These ancient features have an enigmatic origin. The Omega mapping tool on Mars Express revealed that there are places with a lot of sulfates, which could be formed from the evaporation of shallow lakes or from rain that involves. Craters in permafrost are frequently observed. Lobat ejecta deposits surrounding the impact crater, left, are likely attributable to subsurface material abundant in ice. The crater's diameter measures 10 kilometers. The diagram shows the moment of impact when the temperature rises, causing ice to melt. This creates a mix of water, ice, and water vapor, forming a hot, glowing substance. Subsequently, after retreating, the ejecta traverse the surface for a considerable distance, resulting in the formation of the visible lobes. Lobate ejecta craters indicate the properties and condition of the subsurface material during impact events. Meticulous examinations of their morphology can yield insights into the depth and ice composition of the permafrost. Mars has an average yearly surface temperature of minus 70 degrees Celsius, much lower than the freezing point of water. However, stable ice formations are only found in the Earth's polar regions. In tropical latitudes, frost sometimes forms before sunrise and quickly melts as morning temperatures rise. When the sun heats the surface, the lowest atmospheric layer becomes sufficiently desiccated, so ice melts even at sub-zero temperatures. In winter, in mid-latitude regions or on shaded inclines, ice may persist for weeks, but it will become unstable at the surface when spring warming begins. However, if the ice is relatively insulated from the atmosphere, such as under a layer of dust, and temperatures remain low enough, in certain parts of Earth like northern Siberia or Canada, similar conditions cause subsurface material to be frozen to depths of several hundred meters, a phenomenon called permafrost. Could Mars have ice-rich permafrost? Several observations support this idea. While most solar system impact craters have radially ejected material around them, several Martian craters have ejecta with a lobate morphology similar to mudflows. These craters provide strong evidence of ice-rich permafrost under the Martian surface. Lobat ejecta craters were observed by the Themis camera on Mars Odyssey in 2002. The image on the left depicts a human visible crater in the Chrysi Planitia region, recorded in visible light. Conversely, the right image features nighttime photographs of craters in the Alcides Planitia region, obtained by the camera's thermal imaging technology. Temperature differences caused by changes in the material and texture of the ejecta help explain what makes each crater unique. The vast ejecta surrounding this type of crater on the northern hemisphere plains indicates the existence of significant quantities of water ice at the time of impact. Even the minutest craters exhibit lobat ejecta, indicating a subsurface soil abundant in ice. Mars possesses subsurface water. Numerous contemporary icy deposits exist above the permeable and ice-laden permafrost. The ice has predominantly been conveyed through the atmosphere, deposited, and then insulated and safeguarded by a layer of sediments, except in polar regions where the ice remains exposed. Permafrost usually starts at 300 meters to 1 kilometer depth in the equatorial regions. It can start between 300 meters and less than 10 meters deep in mid and high latitude areas. In these colder places, temperatures below minus 70 degrees Celsius help keep the permafrost stable near the surface. The permafrost depth is estimated to range from 1 to 3 kilometers in the equatorial zone and from 3 to 7 kilometers in higher latitudes. At the Martian equator, the eastern end of the Valles Marineris canyon system abruptly becomes a large topographical depression, larger than France. In this area, disordered, chaotic landscapes extend outward from the cratered plateau to depths of about 3 kilometers, with some of these depressions being enormous enclosed depressions several hundred kilometers long, mysteriously formed. These landscapes are intricately linked to large, deep outflow valleys. An excellent example is the Hydaspes Chaos region, situated at the Valles Marineris terminus, and characterized by rocky terrain with lofty pyramid-shaped hills, each approximately 1 kilometer in height, distributed uniformly along straight fault lines. One of the main mysteries of their formation is the lack of any fissure or exit that could have ejected the pre-existing material. Generally speaking, this part of the cratered plateau was initially covered by permafrost. When the subsurface material warmed due to volcanic eruptions or climate change, the permafrost melted and part of the terrain collapsed. Another question remains: how did all the solid stuff, sediments and rock debris, move about during this thaw? This area's permafrost was mostly ice and very little rock. The amount of rock would have decreased significantly as the ice melted and the land sank. The idea of ice-rich permafrost is correct. The total amount of water excavated from these rough terrains would be enough to cover the whole planet up to 40 meters. Towards the northeast of Valles Marineris, large, deep valleys cut across the cratered plateau and extend into Chrysoplanitia. Their discovery sparked a lot of interest because it was thought these valleys had been shaped by flowing water or mud. However, they don't look much like the river-valley networks on the cratered plateau, and some of these features are relatively young geologically. The outflow channels have a unique shape. They don't have any tributaries and have a limited geographical origin. Several channels run across the floors of these formations, passing big obstacles like impact craters, forming teardrop-shaped structures that taper in the direction of the flow. The arrangement of these streamlined islands is quite interesting. We estimate the volume of water involved in these catastrophic events by analyzing the widths of the channels. For example, if we assume a water layer 10 meters deep in Ares Vallis, which spans 25 kilometers in width, the highest discharge rate may have exceeded 100,000 cubic meters per second. Meanwhile, alternative outflow pathways on Mars may have experienced discharges of over 70 million cubic meters per second, which exceeds 2,000 times the volume of the Mississippi River. Where did this water come from? We have put forward various scenarios. According to Mike Carr of the U.S. Geological Survey in California, floods in the canals north of Valles Marineris are caused by water stored underground in Mars permafrost, erupting from this reservoir, which could supply about 10 trillion cubic meters of water. The water in Athabasca Vallis and other channels comes from permafrost that has thawed due to lava rising through cracks in the crust. For the internal view of outflow channels, the Pathfinder lander and the small robot rover Sojourner sent a panorama of the Ares Vallis outflow channel in July 1997. The sparse dunes were covered with disordered rocks, and in 1976 Viking 1 had taken pictures of the same terrain about 800 kilometers northwest. This large image from the Viking orbiter, 1976, shows the Pathfinder landing site on a wide level plain free of major topographical features. There is clear evidence of water flow, though, as a butte close to the origin of a streamlined landform. Seems to have been in the middle of a flood. How did these rocks get here? These could have been carried here by the great floods of water or dirt that once flowed through these rivers. Or they could have been ejecta from nearby impact craters or the eroded remnants of the native rocks of this area. All three explanations are plausible. Some of the blocks are triangular and have striations, suggesting the influence of strong wind erosion. See pages 134 to 136. Other blocks have sharp rectilinear ridges, suggesting they are probably ejecta from intense meteoritic strikes. Several blocks in the image intersect or are positioned at angles, suggesting that a flowing liquid may have deposited them. For what reason is the ground colored orange? Numerous languages reflect the planet's color in their nomenclature. For example, Mars was the red one in ancient Egypt, Lohitanga was called red-bodied in India, and blood was associated with Mars, the god of war in Roman mythology. Mars can selectively reflect red light while absorbing violet and blue light. According to analytical chemistry, a thin layer of dust, a few micrometers thick and rich in magnetized iron oxides, magnetite's red arrow, encases all these blocks. The soil has a thin layer rich in magnesium sulfate, which suggests the presence of mineral salts may have been deposited after water evaporated in the past, according to spectrometer analyses performed on Sojourner. Mars has long been considered a rusty planet because of its color, and data from Pathfinder has shown that the soil contains about 17 to 18% ferric oxide, Fe2OK. The soil on Mars is mostly silica, the second most common component after iron, Fe2OK, which accounts for about 43% of the soil. About 20 years ago, Vikings 1 and 2 discovered that the soil on Mars was nearly identical at both locations, indicating that the surface is covered by a thin layer of dust that has changed over billions of years. So what gives Mars its abundance of iron? Analysis of the SNC meteorites from Mars shows that on average, its mantle contains 2.5 times more iron than Earth's. The most likely explanation is that Mars's reduced gravity has rendered the difference between the two planets' soils to be. The valley is crossed by the river Lena and the Martian discharge channels. The Lena River, which is 4,000 kilometers long, has a floodplain 25 kilometers wide downstream of Yakutsk, the capital of the Yakutia Republic in Siberia. Source: NASA, Landsat. The riverbed shows many similarities to the outflow canals on Mars. Both have formed above permafrost and are about the same size, with minor longitudinal gradients and minimal tributaries. Mars-like episodes of violent flow during the Siberian spring suggest possible occurrences there. We call these floods catastrophic, due to the large volume of water. The Lena River's flow reaches 50,000 cubic meters per second, while the flooding in Ares Vallis was estimated to have been as high as 100,000 cubic meters. When the Martian valleys Simud and Shalbatana meet, on the right, a network of waterways forms. Some of these channels split off into other valleys, like Simud, which form long islands. These features are very similar to those in the central Yakutia Siberian flow valleys, where large variations in flow over months or seasons cause a proliferation of channels, forming large valleys with flat, shallow channels. Mars is similar to Siberia in some respects. For example, during the equatorial winter it can drop to minus 100 degrees Celsius, and in the summer it can climb to plus 23 degrees Celsius. In central Siberia, it can drop to minus 70 degrees Celsius, and in summer, it can rise to plus 30 degrees Celsius. Under these severe conditions, low temperatures help to form extensive and persistent permafrost, which is important for the evolution of the landscape because it forms a true carapace as stiff as concrete. The permafrost depth in central Yakutia, the Siberian Sakha Republic, can reach 1,500 meters. We may find similar values on Mars. This 25-meter cliff on the Lena River is part of a larger 25-meter cliff in Siberia that experiences accelerated erosion in its frozen banks during spring. When the river thaws and snow melts together to form a large outflow, it can erode riverbanks by 30 meters in a few months, exposing large ice layers within the permafrost, shown by arrows. Planetologists believe that similar layers exist in the northern hemisphere plains of Mars. The picture shows a hydraulic channel built in a cold chamber by researchers at the University of Orsay to study thermal erosion processes in frozen soil, similar to Mars flow events. Planetologists are trying to recreate the exact conditions under which these processes occurred on Mars and in Siberia in a controlled laboratory environment. Take a look at Mars's current weather conditions. including dust devils, snow, storms, trade winds, and anticyclones. The weather plays a role in shaping Mars's surface dynamics daily, and due to orbital fluctuations, the red planet's temperature has fluctuated over millennia. Spring has arrived in the northern hemisphere of Mars. During the northern winter, a blanket of carbon dioxide snow covers the North Pole. In the southern mid-latitudes, dust storms rage beneath the pale rings of ice crystal fog caused by depressions that unleash strong winds that lift fine mineral dust. At present, Mars is in a state of metamorphosis, driven by its seasons and climatic variations. Astronomers have known about the Martian polar caps shrinking in spring, changed cloud patterns, and even variations in surface color since the 18th century. These observations did not surprise them, but they did support the view that Earth is the prototypical planet. Additionally, they noticed that Mars spins on its axis for a period similar to Earth's day, 24 hours and 40 minutes. In addition, the obliquity angles of the equatorial planes of the two planets are nearly identical concerning their orbital planes, 25.2 degrees for Mars and 23.4 degrees for Earth. Mars, like Earth, has 4 seasons. But one Martian year consists of 669 Martian days, equal to 687 Earth days. Nevertheless, these similarities did not lead ancient astronomers to call Mars another Earth. The Martian year is the length of a year on Mars. Although Mars follows a seasonal cycle like Earth's, its eccentric orbit makes the year longer. At perihelion, the point in Mars' orbit closest to the Sun, which happens every year after southern spring, the planet is about 20% closer to the Sun than in the opposite season. As a result, Mars receives about 50% more solar energy. The planet's velocity is maximized at perihelion, leading to noticeable differences in the length of its seasons. The southern summer is hot but brief. The map shows surface temperatures of Mars's southern hemisphere, as measured by the Themis infrared camera, which is part of the Mars Odyssey mission. The color red indicates daytime temperatures, and blue indicates nighttime temperatures. At the South Pole, a carbon dioxide snowcap that was visible last winter still exists, with a record of -125 degrees Celsius. During a nice afternoon in the southern summer on Mars, temperatures may reach a mild 20 degrees Celsius with a light trade wind. But it gets very cold at night, with temperatures falling several degrees to -100 degrees Celsius, and staying there until dawn. See temperature chart on page 124. The soil on Mars is dry and granular, and it doesn't hold much heat and much less thermal inertia than Earth's surface, especially its oceans. And because Mars has a tenuous atmosphere, temperature fluctuations are much more noticeable. So Mars has a hypercontinental climate. Mars's seasonal cycle is much more pronounced than Earth's, especially at solstices, when the alignment of the planets guarantees that one pole will be exposed to the sun all day long, with the summer pole absorbing the most solar energy. On Earth, the North Pole never gets hotter than, say, Viking 1, the first interplanetary weather station, which records Mars' temperature and transmits it directly from Planitia due to the thermal inertia of ice and oceans and the reflective qualities of ice and snow. At 1.6 meters above ground height, these instruments recorded temperature, wind speed, and pressure from July 1976 to August 1979. After northern autumn, see diagram, the average temperature dropped gradually until the winter solstice. 2 global dust storms drastically reduced the amplitude of daily temperature fluctuations. During the day, the suspended dust obstructed sunlight, and at night, it emitted infrared radiation, limiting surface cooling. This effect is similar to the effect of clouds on Earth. Temperatures are more moderate under overcast skies compared to clear skies at night. Mars is little affected by Death Valley, California. where daily average temperatures reach their highest point in the summer hemisphere's polar region at the solstice and gradually drop as we move from the summer to the winter pole. On the other hand, a more typical situation develops during the Martian equinoxes. Cold polar regions and warm regions near the equator. For a long time, astronomers assumed that Mars's atmosphere consisted of nitrogen, like Earth's, based on precise measurements. However, they failed to account for the effect of dust, which gives the impression of a thick Martian atmosphere. So, they were shocked in 1965 when, while orbiting behind Mars, Mariner 4 sent signals revealing that Mars has an extremely thin atmosphere and an average surface pressure of about 6 hectopascals, comparable to Earth's air pressure at about 30 kilometers high. Since 95% of Mars's atmosphere is carbon dioxide, which is toxic to humans, living at such low pressure requires a pressurized spacesuit. These main elements make up Earth's and Mars's atmospheres. We are looking at the mean temperature profiles of Earth and Mars. In the lower few kilometers of both planets, most of the atmosphere's mass is located in the well-mixed troposphere, where temperature drops sharply with increasing altitude. Between 20 and 60 kilometers, Earth's atmosphere is warmed by a substantial ozone layer due to the absorption of ultraviolet radiation. On the other hand, Mars has a negligible ozone layer, and its thermal profile stabilizes between 60 and 120 kilometers, which is warmed by the absorption of near-infrared solar radiation. Above 120 kilometers, in the thermospheres of Mars and Earth, the sparse molecules are hit by intense ultraviolet radiation, which fragments them and raises their temperature. The thermosphere's temperature shows large daily and seasonal fluorescence fluctuations. The Viking missions, 1976, determined the other main components of the Martian atmosphere. In situ measurements confirmed the presence of the transparent and neutral gases nitrogen and argon. Traces of oxygen, O2, exist in negligible quantities compared with the oxygen content of the Earth's atmosphere, resulting from photosynthetic activity in plants and bacteria. So, on Mars, oxygen derivatives, such as ozone, O3, produced by photodissociation in the ultraviolet rays of the sun, are rare. Such a small amount of atmospheric ozone offers no protection from ultraviolet radiation. Mars has no ozone layer. Therefore, this radiation can dissociate atmospheric CO2 into oxygen O2 and carbon monoxide CO molecules. Why Mars' carbon dioxide has not all been thus converted has long been a subject of debate. As far as we know, the small amount of water vapor in the air, see pages 149 to 151, provides the reactive agent OH, which causes CO to quickly oxidize, recombine with O2 to form CO2. This ensures that carbon monoxide and oxygen remain smaller than carbon dioxide, see table opposite. Mars Express and its SPECAM spectrometer, capable of measuring amounts of ozone and water vapor, have increased our knowledge of this atmospheric chemistry. Another spectrometer, PFS, surprised researchers by detecting traces of methane, CH4. Researchers asserted that this discovery pushed the instrument to its limits, but subsequent, and equally challenging, spectroscopic observations from Earth validated this. Is methane's instability in the Martian atmosphere necessitates the presence of a subsurface source, which could be evidence of ongoing volcanic activity? Could there be evidence of life existing underground? Low ground. The two main factors that interact to generate winds on Mars and Earth are differences in temperature. The main driver of atmospheric dynamics is the temperature gradients caused by solar radiation. As heated air rises and expands, the air density at lower levels rises above the surface pressure. As a result of these thermal disparities, pressure gradients at altitude form, and winds are generated to transport air masses from higher pressure regions, warmer areas, to lower pressure regions, cooler areas. The figure shows atmospheric thermal variations on Mars, with average northern hemisphere winter solstice temperatures in degrees, as measured by the TES spectrometer on the Mars Global Surveyor. Since the summer hemisphere air is denser than the winter hemisphere air, the summer air is pushed toward the winter hemisphere at higher altitudes. Hadley circulation, named after the English physicist who first explained the process in 1735, is how warmer regions induce meridional north-south circulation. This circulation carries air masses toward cooler regions at altitude, where they cool and descend. Then the air masses cool and descend even further, and the lower atmospheric layers redirect the air masses back toward warmer regions. The atmosphere forms pairs of cells around the planet, one in each hemisphere and the intertropical zone. Unlike Earth, where Hadley circulation is limited below the stratosphere, preventing vertical circulation, Mars usually has a single extensive Hadley cell that crosses the equator and both hemispheres. The Martian cell is much more prominent at high altitudes than its terrestrial counterparts. Winds in the Martian atmosphere are generated by meridional circulation and the planet's rotation. On a rotating planet, meridional south-north air movements produce strong lateral easterly or westerly winds that dominate atmospheric circulation. This occurs because, near the surface, at the base of the ascending branch of the Hadley cell, air follows the planet's rotational axis. As the air is drawn toward the equator in the upper cell, it moves away from the axis of rotation. Like a skater extending her arms while spinning, these air particles rotate more slowly than the planet, resulting in retrograde winds that blow from east to west. As they approach the pole, the air masses near the axis of rotation begin to rotate faster than the planet, akin to a skater pulling in her arms and F. Planetary rotation also influences air movements. Planetary rotation also affects air movements. D. Mars has almost identical rotation periods and similar seasonal variations in insolation. The red planet exhibits meteorological elements unlike Earth. So, Mars has its westerly winds at around 50 degrees north, a jet stream, like the high-altitude current circling the Earth from west to east at mid-latitudes in both hemispheres, tropical trade winds, etc. At least that is what we deduce from the scarce data provided by infrared detectors and the Viking landers. Computer models of the Martian atmosphere help us analyze and interpret this data. Such studies also reveal fundamental differences between atmospheric circulation patterns on Earth and Mars. The absence of oceans on Mars is a factor here. On Earth, the lower layers of the atmosphere are generally warmer in the tropics than at the poles, while on Mars, for most of the year, the thermal contrast is between the spring-summer, warm hemisphere and the autumn-winter, cold hemisphere. This phenomenon is due to the hypercontinental nature of the Martian climate. Although around the equinoxes, a more Earth-like situation pertains, and it is colder at the poles. In addition, the contrast in temperature between the hemispheres is heightened because of dust in the atmosphere, which absorbs solar radiation directly in regions where insolation is greatest. For a climate expert on Earth, Mars's meteorological chart might not look as extraterrestrial as one might think. The dominant wind patterns are the same on both planets. At the latitude of Europe, for example, winds mostly come from the west, impacted by the weekly cyclical movement of anticyclones and depressions, which are low-pressure and high-pressure systems, respectively. A chart depicting mean surface winds on Mars during the northern winter solstice, produced by a computer model at the Laboratoire de Météorologie Dynamique in Paris, at latitudes similar to Europe, 35 degrees to 75 degrees north. The jet stream on Mars affects the surface in a way that's similar to Earth. The winter winds on Mars mainly blow from the west, especially in higher areas. Further south, their turn branch of the Hadley cell impacts both hemispheres in the lower atmospheric layers. Deflected by the planet's rotation, it generates easterly trade winds north of the equator between 0 degrees and 30 degrees B, intensifies upon crossing the equator, and subsequently induces robust westerly jets, reminiscent of summer monsoon winds in India and Central Asia, around 30 degrees south, C. Surface wind streaks are formed yearly by the buildup of light-colored dust in the shadow of features like minor craters, which indicate the direction of the dominant wind. These deposits are most noticeable in areas with darker terrain, especially in two spots next to Alcides Planitia on either side of the Martian equator, shown as white rectangles on the wind chart. Mars's tropical climate is largely continental, like Asia's, with a trading system and monsoon winds comparable to Earth's. Upon closer inspection, the meteorologist will note that Mars is characterized by a very arid climate, which causes strong winds that vary during the day and night due to the large temperature gradient. This effect is not as noticeable on Earth. At night, the atmosphere close to the Martian surface gets very cold, prompting denser gas to flow down slopes and produce strong localized winds until dawn. In contrast, during the afternoon, the warmed air near the surface rises up slopes. All Mars probes have consistently observed these pronounced oscillations. All atmospheric layers are indirectly affected by variations in wind and temperature close to the Martian surface. The daily variations in these variables cause waves to occur either once a day, called diurnal frequency waves, or twice a day, called semi-diurnal frequency waves. These waves are analogous to ocean tides and are called thermal tidal waves. These and other daily wind patterns significantly affect Martian weather and pose challenging problems for meteorologists studying Mars. Solid particles on Mars range in size from a few micrometers, dust, to hundreds of micrometers, sand. Dust storms caused by the wind lifting and transporting the smallest particles, a process called saltation, are displaced from the ground. As winds persist, sand and dust build up to form abundant dunes on Mars. The surface of Mars is characterized by linear dunes and barchans, the former of which can be either straight or crescent-shaped, and the latter by the gradual buildup of material on the leeward flank, which eventually causes avalanches to steepen that same flank. The Martian landscape is characterized by dunes, similar to the ergs of terrestrial deserts, often found in low-lying areas and valley bottoms. While we have not detected any movement of these dunes, our best guess is that they gradually shift over time. Viking and Pathfinder imagery clearly shows that many Martian rocks have been eroded by wind-driven particles, with surface striations and centimeter-sized pits as evidence of this erosion. Wind erosion may not have an immediate and major effect on Mars because of its thin atmosphere, but exposed rocks will greatly affect millions or billions of years from now. The dust cycle. A perpetually dusty atmosphere with orange skies. The sky of Mars, which was first seen as a cloudy grey-blue, was later readjusted to show its actual and unexpected colors: rusty, orange, and salmon pink, caused by mineral dust particles suspended in the atmosphere with a diameter of 1 micrometer. There is no conclusive answer to whether the strongest winds, invisible to future Mars explorers, can lift and support large amounts of dust. However, wind tunnel experiments simulating Martian conditions have shown that winds up to 100 kilometers per hour can displace particles about 100 micrometers in diameter, which then mobilize finer dust that can stay in the air for longer periods before settling, a process called sedimentation. Precipitation events like rain and snow usually remove this fine dust, but it may happen on Mars, though much less efficiently. The dust in the air causes large variations in atmospheric opacity and consequently in average air temperature. At 20 kilometers altitude, even in relatively clear Martian conditions, the temperature is 30 degrees Celsius higher than in an uncontaminated environment This temperature can reach 80 degrees Celsius during dust storms, a level not seen on Earth. During the day, dust on Mars absorbs solar radiation, warming the upper atmosphere and cooling the surface. At night, however, infrared emissions from the dust warm the surface. As a result, dust reduces the temperature difference between the day and night, but has little effect on average surface temperatures. The dust cycle, planet of storms. Planet Earth, a storm-ridden cycle. Mars is traversed by several dust storms every day. Localized storms, everyday events on Mars, and space probe observations raise most dust in the Martian atmosphere. Most of these events happen in areas with low air pressure at high and mid-latitudes or near the changing ice caps. The temperature differences between the carbon dioxide snow and the ice-free ground create strong winds. Every year, dozens of Martian storms attain regional importance, extending across thousands of kilometers. They may last for several days, especially in southern spring and summer. Observations of atmospheric dust tell us that the year can be divided into two distinct periods. A clear season during northern spring and summer, and a dust season, when severe storms occur during autumn and winter. In the clear season, storms are relatively few, and there is not much dust in suspension in the atmosphere. One clear season resembles the next. Typical small storms arise on similar dates, and the usual quantities of suspended dust are observed. However, the major meteorological events characterizing the dust season vary yearly. In some years, one or more truly global storms may shroud the Martian surface for months. The TES spectrometer on the Mars Global Surveyor measures the variation in dust concentrations in the Martian atmosphere concerning latitude. A vacuum atmosphere is shown in violet, and a dusty one is in red. The events during the season of massive storms vary significantly yearly. For example, in 1999, only a handful of regional dust storms were recorded. But in 2001, a global storm lasted for months. The data clearly shows that dust is lifted in local storms near the seasonal polar caps, which appear white, because infrared dust measurements are impossible at low temperatures. Mars dust storms are typically caused by violent winds on the periphery of the seasonal polar carbon dioxide cap. In August 2000, the Mars Global Surveyor observed a dust storm close to the northern polar cap, about 900 kilometers wide, and resembled a dust storm in the Sahara that had occurred a few months earlier on Earth. The characteristics of the two storms were similar. At the back, a central jet formed by the storm with a small area of activity, and at the front a mushroom-shaped cloud of dust was spreading out. A dust cycle. Dust vortices. Observations from Viking in the 1970s and from later probes such as Pathfinder, Mars Global Surveyor, and Mars Exploration Rover revealed that atmospheric dust on Mars is also lifted in the form of vortices, commonly known as dust devils. Researchers believe these events may be much larger than anything we see on Earth based on their shadows on the ground, which are easier to see than the dust columns. Martian dust devils may reach 10 kilometers in height, some tens of meters, or even hundreds of meters in diameter. On Mars, they occur in the afternoon when surface temperatures are highest and atmospheric convection is strongest. A dust devil draws in surrounding air and concentrates it at its center. According to the same principle as that which makes ice skaters rotate faster as they pull their arms inwards, the masses of air sucked in towards the dust devil's axis of rotation are strongly accelerated, resulting in violent transverse winds. Combined with the vertical aspiration at the center of the dust devil, these winds lift large quantities of dust. We still need to discover the exact proportion to which these dust devils contribute to the dust supply in the Martian atmosphere. One highly visible feature of the planet's surface is the innumerable graffiti scored across it for enormous distances by dust devils. See images below and on the facing page. The ground that a dust devil has cleaned typically appears darker than the fine dust surrounding it, making these tracks simple to see. Storms on Earth's surface. The dust cycle. When the world disappears under a cloud of dust. During the summer of 2001, a massive dust storm formed on Mars in late June, moving toward Hellas. In 2 days, it covered about 4,000 kilometers before crossing the equator and causing dust upsurges in different areas. The planet was obscured by dust until the end of September, as shown in the 2 NASA Hubble Space Telescope images up top. And subsequent analysis revealed that this was not a global event, but a series of localized dust upsurges in specific locations. How does a local dust storm become a planet-wide event? The mechanism is as yet poorly understood. What we do know is that the lifting of dust into the atmosphere causes considerable meteorological changes. By absorbing the sun's rays, the dust warms the atmosphere locally, creating or increasing temperature differences, the driving force behind winds and atmospheric circulation. On the global scale, a little dust lifted into the tropical atmosphere of Mars' southern hemisphere, where many local dust storms occur during summer, intensifies the circulation within the Hadley cell, and thus the trade winds, see pages 128 to 133. Models show that this strengthens the winds, especially in the southern tropics. These winds pick up more dust, and the dust causes stronger winds. The machine fuels itself. This kind of mechanism also operates on a local scale. A combination of local and global phenomena likely triggers global storms. In light of these facts, why do such storms occur in some years and not others? The answer is still elusive. During the southern spring, when Mars is almost at perihelion and insolation is at its highest point, the southern hemisphere experiences several local and regional dust storms. A handful of these storms can intensify yearly into a global dust storm, a meteorological phenomenon unlike any other in our solar system. In this particular event, dust covered almost all of Mars for months. In 1956, astronomers observed the first events when Mars was closer to Earth than usual. Astronomers were surprised by the extent of the phenomenon and disappointed at being unable to see anything through it. The famous American popularizer and champion of astronomy, Carl Sagan, wrote that at the time Mars was about as fascinating as a baseball with no seams. The phenomenon was recorded again in 1971 as the American probe Mariner 9 and then 2 Russian probes, Mars 2 and Mars 3, went into orbit around the planet. They were witnesses to the most intense global dust event ever seen. As the dust began to settle, Mariner 9 was still operating and managed to secure photos of the surface. See pages 187 to 189. During the next Martian year, 1973 on Earth, another planet-wide storm occurred. And no less than 2, 100 days apart, were unleashed during the first year of Viking's 1977 mission. There were no similar events during the next 2 Martian years. But in Viking's 4th year, 1982, they recorded another global dust storm. Nearly 20 years had passed since the next event when the Mars Global Surveyor told us about a new global storm. The 1970s saw the greatest concentration of such storms, as recorded between 1956 and the present. Why should that decade be so exceptional? The answer may depend on how astronomers observe the planet and space missions rather than climatic anomalies. As it happens, 1971 and 1973 were years of better visibility during the storm season. As was 1956. Resolution was good. The geometry of the 2 planets' orbits lends itself to more favorable observations at intervals of about 16 years. Martian water cycle. Vapor, frost, and ice. Water vapor is carried by the Martian atmosphere by clouds and mist. Even though Mars doesn't have any oceans or canals, it still has a lot of water on its surface and shows signs of a seasonal water cycle. The TS spectrometer on board the Mars Global Surveyor spacecraft tracked the annual water vapor cycle, defined as the variation in the amount of water vapor present in the Martian atmosphere as a function of both seasonality and localization. This variation is quantified in terms of precipitable micrometers, which indicate the depth to which the water would sink if all the vapor were to settle to the surface. NASA, JPL and Marlin Space Science Systems supply a vast expanse of water ice, sediments and dust that forms the northern polar cap, a vast glacier with winding troughs. Encircling the cap is a layer of mostly pure white water ice that interacts with the atmosphere. Atmospheric water vapor is produced as the cap warms in the winter. The surface of the cap has been shaped into a terrain of depressions, hills and knobs, about 20 meters wide and 2 meters deep by these atmospheric interactions. The North Pole is the starting point for all phenomena. A large glacier formed over time of water, dust and sediments has warmed its icy surface in the summer, because the atmospheric pressure on Mars is too low to allow water to exist as a liquid. Instead, the ice melts into the atmosphere directly. During a few summer months, the air currents redistribute water vapor from the North Pole to different parts of the planet. The amount of water involved is not great. If all the water in the Martian atmosphere fell to the surface, there would be enough to form only a few tens of micrometers of ice in the wettest regions. Despite the comparative lack of water in the atmosphere, saturation is often reached at such low temperatures that clouds form and frost can appear at the surface. Water vapor can also diffuse into the porous regolith, forming the planet's uppermost layer. This set of processes represents Mars's water cycle. Does the water periodically return to its initial state as ice in the North Polar Cap, or is the cycle closed? And the reply is yes, but for there exists on Mars an area where water condenses but never leaves, the South Pole. This is due to a layer of carbon dioxide ice permanently covering the southern polar cap. The surface here is at such low temperatures, minus 130 degrees Celsius, that any water present will exist only as ice. The ice cap locks water in a veritable deep freeze. So the long-term water cycle on Mars seems to be a one-way journey, transporting water from the North to the South Pole. Mars could not have maintained this dynamic throughout its history. The North Pole would have had no water. It is very probable that at some time in the past, the cycle operated in the opposite direction. A hydrologic cycle involving clouds, fog, and non-precipitating waterless clouds. Clouds play a significant role in Earth's climate and meteorology because they contribute significantly to atmospheric energy via the release of heat when water vapor condenses into clouds, and because their reflectivity or absorption of radiation greatly impacts the planet's energy balance. The Martian environment is very different from Earth's in terms of temperature, pressure, and water availability. However, planetologists continue to focus on Martian clouds because diverse cloud formations play an important role in Martian meteorology. On Mars, clouds contain ice crystals about 1 to 5 micrometers in size. These crystals will undergo gasification before reaching the ground, and they neither fall fast enough nor accumulate enough to produce rain or snow. Where on the Martian surface can one find cloud cover? Almost annually, from the end of spring into the beginning of summer in Mars' northern hemisphere, a band of clouds visible from Earth encircles the Martian equator. This hazy thing starts at the northern polar ice cap, where much water vapor is released into the atmosphere, which is cold because there isn't much dust. The rising arm of the Hadley cell quickly carries this water vapor to tropical latitudes, where it meets increasingly colder air layers until it reaches a saturation threshold where it condenses. The Martian cloud belt is similar to the intertropical cloud belt on Earth, and its intermittent presence causes what are known as rainy seasons. When the air mass moves closer to the poles in the fall and winter, it cools down significantly and condenses, creating a variety of cloud formations, some scattered and others more structured. This phenomenon is called the polar hood and is more noticeable in the north than in the south. When spring arrives in both the northern and southern hemispheres, the return of daylight after months of polar night reveals a breathtaking sight. A radiant frost layer covers the surface of Mars from the poles to latitude 50 degrees, and this layer gradually moves inward as the season changes. When astronomers first observed the seasonal polar ice caps in the 17th century, they were unanimous in their conclusions. The image illustrates the northern polar cap in mid-spring. This is a photomosaic composed of photos captured by the Mars Global Surveyor at approximately 1400 local time in July 2002. A portion of the cap would consistently reside on the planet's nocturnal hemisphere. The seasonal caps comprise a layer of carbon dioxide ice ranging from 10 centimeters to 1 meter thick, accumulating during autumn and winter and gradually transitioning to gas, sublimation, in spring. The cap measures merely 3,000 kilometers in width, a reduction from its midwinter diameter of 5,000 kilometers. The yearly polar caps additionally encompass a minor quantity of water ice in crystalline structure. In spring, along the periphery of the caps, this water ice sublimates more slowly than the carbon dioxide. This elucidates why snow and frost accumulations resemble those on Earth. It was not until 1966 that their true composition was unveiled. As the examination of data from the inaugural Mars spacecraft, Mariner 4, disclosed that they consisted of frozen carbon dioxide and dry ice. In the polar areas, during autumn and winter, temperatures decrease until they reach the condensation point of carbon dioxide. On Mars, this transpires at approximately minus 125 degrees Celsius, with the value contingent upon atmospheric pressure. The atmosphere condenses, depositing snow and carbon dioxide ice on the ground. In spring, the solid carbon dioxide will once more sublimate, transitioning directly to the gaseous form without liquefaction. In the northern hemisphere, the seasonal CO2 layer begins to thin in the spring and completely disappears when summer rolls around. As the North Pole's permanent ice cap melts, it becomes visible and stays that way until the following autumn when carbon dioxide forms again. The southern hemisphere's winter retreat is less uniform. At the same latitude, CO2 concentrations fall in some places and stay the same in others. Carbon dioxide never completely sublimates in the region immediately surrounding the South Pole. This so-called residual cap represents an unprecedented accumulation of frozen atmospheric gas, a phenomenon never seen on Earth before. An ecosystem that sequesters carbon dioxide, the CO2 cycle. Here we are in April of 1998. The planet's northern winter season is currently underway. Finally, after months of maneuvering, the Mars Global Surveyor has pointed all its instruments toward the planet's surface. The MOLA laser altimeter measures terrain with a precision of just a few meters. In the middle of the Arctic night, it unearths previously undiscovered structures over 10 kilometers tall. Quite quickly, it becomes clear that these clouds only appear with no light. By distinguishing these clouds from those on Earth, atmospheric theoretical models reveal their composition of solid carbon dioxide. Initially, comprehending their formation appears straightforward. When the temperature falls below minus 125 degrees Celsius, the temperature at which carbon dioxide condenses under low-pressure conditions on Mars, the atmosphere freezes, leading to the formation of particles that form clouds. However, it is not immediately clear what all of this process entails. These clouds differ greatly from the water-based ones on Mars or Earth. The atmospheric concentration of water vapor imposes size restrictions on water cloud droplets. The principal component of Mars' atmosphere, carbon dioxide, is abundant in carbon dioxide clouds. The Martian surface experiences CO2 blizzards when a section of the atmosphere is rapidly cooled, like when the wind rises over topographical relief into colder strata. A large amount of carbon dioxide ice has solidified on the surface, and the falling snowflakes will make it even better. No matter where you are, the polar cap will always trap around 30% of the air. The effects of this condensation-sublimation process are felt all over the globe. From the sublimating cap to the condensing cap, a CO2 flow is initially generated. This is a crucial part of Mars's atmospheric movement. Secondly, it affects the planet's surface pressure by causing variations in the total mass of the atmosphere that occur during the seasons. The polar caps cause variations because some air condenses there. During the winters in the south and north, when the atmosphere partially freezes on one of the polar caps, the data from Viking 1 showed 2 minima. In the southern winter, there is a drop in pressure due to increased CO2 condensation. Due to Mars's eccentric orbit, the winter in the south lasts longer than in the north. Would Mars be able to host CO2 ice clouds? It is not only during the Arctic night that clouds of carbon dioxide form. At a height of 100 kilometers, the Mars Global Surveyor detected a white layer that might contain tiny particles of solid carbon dioxide in suspension. According to temperature profiles, left, taken by the Pathfinder mission in 1997 and recorded by the SPIXAM instrument on Mars Express, the high-altitude atmosphere can reach the condensation point of CO2 even in tropical regions during summer, courtesy of NASA JPL Marlin space science systems. In areas with very low temperatures, very thin clouds form, according to SPL-CAM's findings. The tenuous composition of these clouds often prevents spectrometers from directly analyzing them. Changes in atmospheric radiation have been detected by the Omega imaging spectrometer on board Mars Express. Carbon dioxide-based atmospheric ice particles cause such a change. Changes in carbon dioxide ice levels, the CO2 cycle. During the CO2 ring, carbon dioxide snow melts and turns into liquid water on the southern hemisphere's dunes. As the sun rises in the spring, the ice sublimates, revealing dark blotches on the surface. Scientists believe that powerful carbon dioxide gas jets carry sand and dust in these blotches. Researchers examining data from NASA's Mars Odyssey orbiter observe explosive eruptions near Mars's south polar ice cap every spring. Here we see jets filled with dust soaring into the Arctic sky. The snow-covered high latitudes of Mars are some of the most breathtaking and distinctive features in our solar system. When illuminated by the spring sun, satellite images of the polar caps have revealed strange structures, but their origin and evolution remain unknown. It isn't easy to imagine the ice mantle's configuration from a close-range perspective. As the air condenses into ice and snow on Mars, there are probably not many entrapped CO2 bubbles in these materials. In some places, layers of carbon dioxide ice get very thick, consistent, and see-through. Any microscopic dust particle sublimated into the see-through ice will heat up as it absorbs the spring sun's rays and may even form a gas bubble around itself. Sublimation from below can also occur if the stony substrate beneath the ice is heated by the sun. In some places, spring ice may float on top of a cushion of pressurized air. If a crack forms in the ice cap, the forces below could cause a big eruption of dust and gas onto the cap's surface. These are insects that inhabit the polar regions. In the spring, geysers of dust and carbon dioxide spew forth from the cap in some areas close to the South Pole. You can identify them by the dust they blow away from them. Solar radiation heats the rocks beneath the ice, releasing gas into the transparent ice, which most likely originates from the melted ice below. The gas's forward motion under the ice makes it look like it's moving. It is powerful enough to chip away at the surface and carry mineral particles across hundreds of meters. Erosion occurs yearly at the same spots, because the geysers' locations are dictated by the local topography. Over time, the soil and rocks in these areas have worn down in stair-step patterns. In the spring, the ice surrounding geyser sites reveals these shapes. When the carbon dioxide ice melts completely in the summer, they are easier to see. Seasonal melting of CO2 snow reveals a steady layer of solid carbon dioxide that stays balanced with its surroundings. However, all the polar CO2 ice disappears in the northern hemisphere during the summer near the southern pole. Planetologists are baffled by this long-lived deposit because it is thin, no more than a few meters thick, which is the same as several years' worth of seasonal condensations. In due time, scientists anticipate that this so-called glacier will either melt away or grow into a larger mass, accumulating even more ice. The ice cap cannot naturally stabilize between these options without discovering a feedback mechanism. A competing theory suggests that the remaining southern cap periodically forms in reaction to long-term climate changes in the CO2 cycle. However, the reality of these occurrences is still up for debate. A thin layer of CO2, carbon dioxide. The photo shows a thin layer of carbon dioxide ice on top of a water ice foundation. The spectrometer took these false color images in 2004 during the southern summer. By employing infrared spectroscopy, Omega can distinguish between ice composed of water and ice composed of carbon dioxide. Overlaying the blue water ice is a thin layer of pale pink carbon dioxide ice that extends several meters. Why is there only one remnant ice cap in the southern hemisphere? As expected, a permanent CO2 cap would form in the coldest areas, where CO2 ice is most stable. Neither pole has this cap. Even though the southern summer is hotter than the northern summer, Mars's current orbital eccentricity causes it to last shorter. The ice cap near the South Pole might become more stable. This scenario evolved over time. One could imagine the inverse situation thousands of years ago, with the southern ice cap emitting water vapor and the northern one saturated with carbon dioxide. The planetary climate is determined by vapor orientation concerning the Sun. Planetary obliquity, the angle between the axis of rotation and the perpendicular to its orbital plane, is one of the orbital features that can change to affect a planet's climate. Even though the Moon stabilizes Earth's obliquity, its little variations have contributed to glaciations. Recent studies reveal that Mars's obliquity has experienced significant fluctuations, with extreme values ranging from 0 degrees to over 60 degrees and a pseudo-period of approximately 100,000 years. Mars has a long history of dramatic climatic shifts. Its current obliquity is 25.2 degrees. To what extent do these variants differ fundamentally? The seasons don't stand out as much. Because the Sun remains low in the sky through the degrees of the year, the poles, which have smaller seasonal CO2 ice caps, receive less energy than the rest of the planet. Polar regions experience cooler temperatures. So, as CO2 ice, now at the South Pole, refer to preceding pages, rises, the proportion of the atmosphere CO2 is likely to remain constant. The result is a less dense atmosphere. This study looks into how obliquity affects Mars's weather. A. Very low obliquity, 40 degrees to 60 degrees. B. Great obliquity, 27 degrees to 40 degrees. And C. Low obliquity, 0 degrees to 20 degree. A few million years ago, Mars's tropical regions had glaciers. On the lower slopes of the massive Martian volcanoes in the Tharsis region and the adjacent plains, yellow on the map, structures resemble certain deposits made by large glaciers on Earth. At this point, practically all of Mars's massive glaciers have melted away. However, the HRSC camera on Mars Express detected a rock glacier, A, close to the Olympus Mons scarp. This ice-encased glacier resembles those found in the Antarctic's dry valleys, B, similar to Mars in that they are frigid and dry. If the only places on Earth where surface ice remains stable are the poles, how did glaciers form there? According to computer simulations of Mars' environment, when obliquity was high, there was much more water vapor in the atmosphere than now. Westerly winds propel this humid environment onto the slopes of volcanoes, causing rapid cooling. Ice precipitation impacted the surface. Over millennia, several millimeters estimated annual accumulation rate could have formed a glacier. A small amount of ice may remain at the base of the rocky glacier, protected from the elements by the rock and dust surrounding it, even though most of the water has evaporated. Once the obliquity is greater than 27 degrees, seasons stand out more. The deep ocean gets hotter when the mean insolation at the poles is higher yearly. The pores in the Martian subsoil release the adsorbed CO ice until the reservoir runs out. We don't know how much this reservoir can hold, but imagine a dCO2T 2 times higher. Seasonal variations would be amplified by the increased circulation in this atmosphere. The atmosphere could lift and maintain large amounts of suspended dust. Ed dust. In summer, the polar ice storage would warm up considerably, releasing a lot of water. The hydrological cycle, which includes clouds and frost, would be much more active than it is now. When obliquity is greater than 40 degrees, glaciers form. According to Martian environmental simulations, melting the remaining polar ice would cause a huge outflow of water vapor into the atmosphere, condensing and precipitating faster than it could vaporize. If the poles had ice formed them, these areas could have formed glaciers. Model predictions have come true, with glacier remnants found in places like the Hellas Basin and on the slopes of the massive Tharsis volcanoes, Mars's ancient glaciers. In the past, scientists had found evidence of glaciers in certain places on Mars, before computer models predicted that the planet would have glaciers due to changes in its orbital parameters and axial tilt. Extensive valleys with a unique morphology, measuring 5 to 10 kilometers in width and 1,000 meters in depth, are found at the interface of the cratered highlands and the lower northern plains. Along the axis of the valleys, you can see their flat surfaces. The score marks, formed by alternating ridges and crevasses, start at the walls of the valleys and contour inward to follow the valley's longitudinal slope. They prove the existence of a mixture of ice and rocks that once had flow similar to Earth's glaciers. Rock forms the moraines. The glaciers carried rock debris from the valley walls to form the moraines. These moraines resemble those found in ancient glaciated valleys on Earth, despite the ice melting in some of them. The ice sheet, around 1 kilometer thick, has worn away the surface. Given the red planet's weak gravity and the gentle valley gradient, the ice on Mars must be at least that thick to initiate glacial movement. In light of Mars's atmospheric conditions, what processes may have contributed to the development of these glaciers? These ancient glaciers did not all form due to precipitation in the air. Sometimes, water is pumped out of a pressurized underground reservoir, flows to the surface, and freezes. In October 2001, new sensors were installed on Mars Odyssey, a spacecraft that had just joined Mars Global Surveyor in orbit around the planet. Neutron detectors allowed the gamma-ray spectrometer, one of these instruments, to function. Neutrons and protons are the building blocks of atomic nuclei. By tracking the Martian neutron flux, the neutron detector revealed the presence of water beneath the surface. Nucleons are produced when subatomic particles interact with energetic cosmic rays, which can originate from various sources. As a result, space probe detectors can collect and study the neutrons Mars produces continuously. The amount of neutrons released from a specific location can reveal whether or not there is ice near the surface of Mars. These particles must travel through various Mars subsurface layers before escaping into space. Water used in nuclear reactors has the property that the hydrogen in water molecules significantly slows them down when they travel. The neutron flux's strength decreases as the surface ice rises. When sensors on Mars Odyssey sent back data showing that, in some spots, large quantities of water are frozen at the surface down to a depth of 1 meter, it shocked everyone. Results show that at latitudes greater than 60 degrees, ice concentrations make up more than 70% of the subsurface material. A real layer of ice is probably just a few millimeters below the dry surface. Even though Mars Odyssey can't detect ice more than a meter deep, it could be hiding below latitude 40 degrees. Where does the icy layer on Mars come from? Some scientists believe the ice formed because water vapor diffused into the subsurface's pores. On the other hand, many people think that the ice concentrations that have been observed make it more likely that Mars was once covered in ice at mid and high latitudes. This situation is based on climate models that show that water from tropic glaciers doesn't go straight to the pole when Mars's obliquity drops too low values, like it does today after a period of high obliquity. The area above 60 degrees covers both the northern and southern hemispheres, depositing several meters thick layers of dust and ice. The upper part of this layer will sink as the tropical source runs dry, and the water will move northward. The resulting layer of dust would be thick enough to slow down the rate of ice melting. Just a few 100,000 years ago, there was evidence of liquid water. Although it happened billions of years ago, planetary scientists have agreed that liquid water once flowed across Mars's surface. Images released worldwide in 1999 by the Mars Global Surveyor cast doubt on this theory. The probe's MOC camera in the high and mid-latitudes showed systems of gully-like structures with a debris apron at the end, which were mid-latitudes made by water flowing through the area not long ago, maybe even within the last few million years. Has water recently flowed on Mars? This discovery revived that question. Is it flowing right now, or could changes be the cause? Where do these water flow-induced features originate? It is difficult to explain the flow of water in regions where pressure prevents liquid water from existing, and temperatures are below freezing. 3 options are being considered right now. Some scientists have hypothesized that Martian internal heat could heat aquifers below the surface. These may occasionally have surface flows. Because the flow features seem unrelated to volcanic activity, this scenario doesn't explain how they spread out. It ignores that these features are unique to certain dune fields and mountain peaks. Is there a rotisserie effect when the moon is superobliquity? Several present authors have proposed that major planetary obliquity periods obliquely shaped the flow features. Water vapor could have existed above freezing because atmospheric pressure was high enough. In the summer, when the Earth's axis is in its most direct line of sight with the sun, the slopes that face the poles experience constant heating, directly melting any surface ice and melting any subsurface ice. They reach a specific point in their melting process, which leads to subsequent releases. Does the snowpack have melting going on under it today? Some flow features can be seen on terrains partly covered by ice deposits on shaded inclines. Some scientists have postulated that under this ice cap there is moving liquid water. Third diagram, page 176. What causes the water under the ice to flow? Polar deposits can tell us a lot about past weather patterns. A record of climate variations spanning several million years may be preserved by ice accumulation at the North Pole. Telltale signs of past climates, stratified deposits at the poles. Using MOLA altimetric data collected by the Mars Global Surveyor, the bigger picture shows the area around the North Pole. The deposits are 2 kilometers thick and 1,000 kilometers long, with the vertical scale amplified. The Mars Global Surveyor's smaller images show layers approximately 100 kilometers apart, left. Regardless of the distance, the same sequences remain visible. On the outer edge of Chasma Boreal, in the middle of the polar cap, layers of dust, sand dunes, and ice can be seen in a false color image to the right of the image huge deposits, spanning 1,000 kilometers in width and about 3,000 meters deep, encircle Mars's north and south poles. Perpetual troughs form a spiral pattern, dividing the accumulated sediments at the North Pole. The polar cap's composition is revealed by the sidewalls of these troughs. Each layer, which is less than 10 meters thick, has a different lightness or darkness depending on the ice-to-dust ratio. We can reproduce hundreds of kilometers of the same stratification. Variations in orbital parameters deposit multiple layers, indicating a global climatic origin. These deposits provide light on Mars's climatic past, in the same way that ice cores from Antarctica are used to study Earth's past climates. How long is this climate history? If, with the help of glaciers farther south, the polar cap progressively expanded after the last major obliquity, then this cap has records dating back 5 million years. Gypsum and ice make up the sediments. The frozen wastes of the northern polar region are encircled by vast, dark dune fields, the source of which is mysterious. A recent discovery by the Omega mapping spectrometer showed that some dunes contain an unexpected gypsum mineral. This surprising mineral is shown in red in this composite of false color images. The ice looks white. A spot on the ice cap's edge has a lower concentration. Gypsum, a calcium sulfate, is usually made from liquid water. How could liquid water have formed on such a recent landmass near the poles? When the edge of the cap partially melted, liquid water altered the geological layer from which the gypsum most likely originated. This might have happened because the ice was much thicker before. We see liquid water reservoirs forming under polar and glacial ice sheets here on Earth. Remote monitoring and depiction of Mars continued until the 1960s. Although the length of a Martian year was known in ancient times, Mars could not be explored until the invention of the telescope in the 17th century. Terrestrial telescopic observations remain valuable for monitoring the world between space missions or testing new sensors. For example, the Doppler effect of microwave radiation emitted by Mars's atmosphere can quantify wind speeds with a network of radio telescopes like the LRAM interferometer on France's Plateau de Bure. Giovanni Domenico Cassini mapped Mars, identified its polar caps, and determined that a Martian day lasts 24 hours and 40 minutes. Christian Huygens created the first sketches of the planet in 1659. Many researchers continued to study Mars, but it wasn't until 1777 that William Herschel, a musician and organist who became one of the most brilliant astronomers of his time, made substantial strides with the telescopes he built. The fact that he found Uranus in 1781 is what made him famous. Herschel measured Mars's axial tilt obliquity and concluded that the red planet goes through seasons similar to Earth's based on his observations of the expansion and contraction of the polar caps. Clouds, and the fact that stars were obscured by the Martian disk's periphery, led Herschel to conclude that the planet had an atmosphere. Improvements in optical instruments in the 18th century allowed astronomers to painstakingly map the globe and give names to its lighter, seas, and darker, continents, areas. A red letter indicated that it was 1877. American astronomer Asaph Hall found Mars's 2 moons, Deimos and Phobos, when Mars was relatively close to Earth. The charts made by Giovanni Virginio Schiaparelli, director of the Milan Observatory, are on par with modern charts. He made several observations, many of which are still relevant today. Rectilinear features, which he dubbed canal, were the focus of his most striking findings. Inaccurate translations, which rendered his channels as canals in English and canaux in French, led people to believe they had an artificial origin. In 1896, the idea enchanted the mind of the wealthy American Percival Lowell, who set up an observatory in the mountains of Arizona. He devised a detailed theory that he maintained until he died in 1916. A sophisticated civilization threatened by drought built the canals. The origin of civilizations was a topic of contention in academic journals all the way up until 1962. The study of Mars progressed slowly with the use of modern astrophysical instruments, such as radiometers, polariscopes, and spectroscopes. The absence of oceans on Mars has been known since 1896. From now on, we'll blame plants instead of water for the dark spots. Scientists focused on the Martian atmosphere in 1920 and found it had very little oxygen and water. By 1947, they had identified only carbon dioxide. Until the space age began, the atmosphere's density remained a contentious issue. When is the best time to look at Mars from Earth? During its 26-month orbit around the Earth, Mars gets very close to our planet. Opposition describes this situation. As seen from Earth, Mars lies on the celestial sphere opposite the Sun. The 2 months preceding and following the opposition provide the best viewing conditions for Mars. Mars appears twice as big in some years as it does in others, see table, because its apparent size at opposition fluctuates due to the eccentricity of its orbit. Optimal oppositions occur around once every 15 Earth years. Mariner 4, launched in November 1964, successfully swooped past Mars at 9,850 kilometers on July 14, 1965, marking the beginning of the successful exploration of the planet. Although it came close, Mariner 4 was not the first spacecraft to reach Mars. Mariner 4 returned the first images of Mars to Earth, although the Soviet spacecraft Mars 1 had already flown by the planet. The NASA spacecraft, with a camera on board, transmitted 24 pictures of ancient Martian landscapes. Because Mars lacked canals, Martians, and craters, it was as barren as the Moon, causing disappointment. Indirect analysis of atmospheric characteristics found surface pressure below 7 millibars, which is far more precarious than even the most gloomy predictions had predicted. In what ways are we able to reach Mars? Launched from Earth into a solar orbit, spacecraft eventually reach Mars orbit, which is close to the point of aphelion, the furthest point from the Sun. This method reduces fuel consumption. After the first thrust, the motors stop working except for small changes to the trajectory. Because Mars and Earth advance at different speeds, the launch must occur during a precise launch window, 3 to 4 months before opposition, when Earth is at its closest approach to Mars and will overtake it in its solar orbit. Similar to competitions, launch windows occur every 26 months and last a few weeks. Depending on the rocket's launch year, a journey to Mars can take 5 to 11 months. Before entering solar orbits, the Mariner 4, 6, and 7 probes could only conduct flybys of Mars. Future missions to Mars could use retro rockets to slow down, allowing them to land on the red planet, or at least enter its orbit using aerobraking. NASA's use of powerful launch vehicles to place the 980-kilogram twin probes Mariner 8 and Mariner 9 into orbit around Mars in 1971 and 1972 reawakened interest in the red planet. Mariner 8, scheduled to be launched by NASA on May 8, 1971, plummeted into the ocean after a Centaur rocket malfunctioned. The results from Mariner 9 have been better. Launched 3 weeks later, it made history as the first artificial satellite from a planet other than Earth. The information gathered by Mariner 9 would reveal the red planet's true, more dynamic features, completely altering our understanding of it. On November 14, 1971, when Mariner 9 touched Mars, the world was engulfed in its worst dust storm in recorded history. The dust storm obscured its entire surface. Once things calmed down, the probe took more than 7,000 images of the Martian surface for an exhaustive photographic study. Geologists found massive glaciers, canyons, riverbeds, and volcanoes on a recently discovered planet. Using thermal infrared and ultraviolet observations, Mariner 9 examined the surface, atmosphere, polar caps, and clouds in the northern hemisphere during the winter and spring. Data collected by this spacecraft has been used by scientific journals for more than 30 years. The Soviet Union sent the first Mars probe, Marsnik 1, into orbit on October 10, 1960. Just 3 years after Sputnik 1, the first artificial Earth satellite, was launched. Marsnik 1 was intended to take photographs of Mars. Still, it failed to enter Earth's orbit. In December 1971, the Soviet probes Mars 2 and Mars 3 finally returned their first images of Mars after 11 long and 8 unsuccessful missions. The United States had previously conquered Mars with Mariners 4, 6, and 7. And Mariner 9's 1971 successes solidified this victory. Soviet hopes were dashed in 1971, when the planet was completely obscured by a massive dust storm. And the pre-programmed Mars 2 and 3 cameras failed to capture storm images of the surface. The extensive discoveries made by Mariner 9 were superior to the few images and sparse data collected by the Soviet probes. The Soviet Union launched 4 spacecraft in July and August 1973 to gain a substantial advantage, taking advantage of the 2-year delay of the Viking program. There were 4 Mars missions, 2 orbiters, Mars 4 and 5, and 2 landers, Mars 6 and 7. The 3.5-kilogram M5, 4 and 5 spacecraft were equipped with scientific instruments to comprehensively view Mars at all wavelengths. The slightly over 600-kilogram Mars 6 and 7 landers analyzed the atmosphere's chemical makeup using a mass spectrometer and a suite of meteorological sensors. We thought the Mars quartet would find a lot. It was unfortunate that the gremlins were ready to attack. A few weeks before launch, we discovered defects in the craft's microchips during production. After passing on the opportunity to fix this, we decided to proceed with the launch. Mars 4 and 7 have become lost in space after deviating from their planned paths. Mars 6 touched down without incident, but subsequently cut off all contact with Earth. Additionally, all data transmitted during descent was rendered useless. Martian 5 successfully entered Mars orbit, reached Marsa 22, and stopped transmitting. After several setbacks, the Soviets finally decided to abandon their Mars initiative and shift their attention to Venus. Since no other missions have ever landed on Venus, taken pictures of its surface, or performed analyses of its composition, the decision was beneficial. Soviet spacecraft sent additional probes to Mars in 1996 and Phobos in 1988. Phobos 2 was partially successful, while Mars 96 and Phobos 1 were both unsuccessful missions. Were there obvious anti-Soviet tendencies on Mars? Following the success of Mariner 9 in 1971, NASA set out to place a module on the surface of Mars. Jet Propulsion Laboratory, JPL engineers saw that the Soviet Union had successfully sent spacecraft to Venus, an apparently more hostile planet, but had failed miserably in sending such missions to Mars. As a result, NASA meticulously planned the Viking missions. On August 20th and September 9th, 1975, 2 identical spacecraft were launched, weighing 3,527 kilograms. They included a lander that weighed more than a ton and an orbiter similar to the Mariner. This was one of the most complex and costly explorations ever undertaken by NASA. The meticulous planning that went into the 10-month mission to Mars ensured its successful execution. On June 19, 1976, Viking 1 successfully entered Martian orbit. The instruments used for the mission, including cameras, infrared radiometers, and water vapor detectors, were aimed at finding the perfect landing spot, which was defined as not excessively elevated, not excessively windy, not excessively inclined, not excessively rocky, not excessively dusty, and not near the pole. However, finding such a spot from orbit was impossible, so the landing had to be rescheduled from its original July 4th alignment with the American bicentennial. Finally, national pride was satisfied in 1997 when Mars Pathfinder landed. Viking 1 touched down safely on Chryse Planitia at 22 degrees north on July 20th, the eve of Belgium's National Day. Viking 1 narrowly avoided a large boulder that could have instantly ended the mission. The mission's primary goal was to seek out alien life, although images of Mars from the surface attracted much media attention. Despite the official mission declaration of no life, the scientists overseeing the Viking studies could not reach a consensus as time progressed. Viking 2, like its predecessor, successfully landed on the Utopia Plain, located at 48 degrees north latitude on the opposite side of the planet. The results of the plant run were also consistent. Even so, the Viking mission was successful. The modules only lasted 90 days but were reliable for over 6 years. Last Transmiss Viking 1 received its last transmission. Viking 1 enabled additional surface and orbital studies of Mars's features. We owe a large chunk of the data to the Viking missions, even though Viking did not significantly improve our understanding of Mars compared to Mariner 9. 1975 was the year that the Viking 1 lander and all of its parts were being assembled. Orbiter 1 sent the Viking 1 lander a lighting sea. With its thermal shields in place, Viking sped through Mars's atmosphere at over 4 kilometers per second before touching down. At an altitude of 6,400 meters, Viking released a massive parachute that was 18 meters wide, fitting for the tenuous atmosphere of Mars. In the last few hundred meters of its descent, the lander was guided by the onboard radar and decelerated by retro thrusters, much like the lunar modules. Both spacecraft were thoroughly sterilized before leaving Earth by a 1968 international treaty meant to protect the Martian surface from contamination. The module had a plutonium-based radioactive source that powered its parabolic antenna, which could communicate directly with Earth or through the orbiters. The Viking lander's scientific arsenal included a mass spectrometer, an X-ray fluorescence spectrometer for chemical analysis, meteorological instruments, and cameras. Rarely does a goal present such a formidable obstacle. Only 4 of the Soviet missions were even somewhat successful. Mars 96. In 1996, they launched Mars 96, the final mission. With a weight of more than 6 tons and 4 successful landings, the spacecraft was an ambitious undertaking. Shortly after takeoff, the mission plunged into the Pacific Ocean near the coast of Bolivia after losing contact with Earth's orbit. The 9 successful missions cannot conceal that the United States experienced 5 major failures. The 2 Deep Space 2 soil-penetrating microprobes and the Mars Polar Lander and Mars Climate Orbiter were lost to NASA in 1999, causing major setbacks for the agency. Similarly, after a lengthy orbit around the Sun, the Japanese Nozomi probe, also launched that year, reached a similar conclusion. 1998. Nozomi encountered its first problem when a malfunctioning propulsion system valve blocked its injection trajectory toward Mars. Nozomi would have been near Mars in late 2003, according to an extended flight plan cleverly devised by Japanese mission controllers. However, a major solar flare in April 2002 caused electrical and heating system impairments, leading to the mission's halt. The spacecraft went missing in December 2003 after its fuel froze, rendering it incapacitated. Countless other mishaps could have occurred, including 7 failures at the crucial launch time, of which Nozomi was only one. One operator mistakenly programmed the insertion from Earth orbit into a Mars trajectory for 1.5 years instead of the intended 1.5 hours, leading to the disintegration of the Soviet spacecraft. Cosmos 419 in 1971. This operator's error had a significant impact on the incident. as a result of a miscommunication between the two teams using different units of measurement for trajectory correction instructions. The Mars Climate Orbiter broke apart upon entering orbit at 57 kilometers rather than the intended 120 kilometers. In 1993, the Mars observer went missing just before entering Mars orbit, demonstrating how a radio blackout could lead to unknown failure causes. The Mars Polar Lander and Beagle too vanished on their way to Mars in 1999 and 2003, respectively. On rare occasions, mistakes lead to new understandings. For example, as the Mars Global Surveyors, MGS, spacecraft traveled across altitudes below 120 kilometers, its magnetometer detected magnetic anomalies in the Martian crust. Due to its inability to detect anomalies, the magnetometer was originally designed for the Mars Observer, a large vehicle intended to operate above 350 kilometers. After the tragic loss of Mars Observer in 1993, the mission's successor, MGS, a smaller probe meant to orbit Mars at low altitudes and detect magnetic fields via upper air resistance aerobraking, installed a backup magnetometer. However, the story did not end there. MGS had to use a progressive braking maneuver due to damage to one of the solar panel supports. We made sure to map all anomalies by increasing the frequency of low-altitude sweeps. It took another 17 years after the Viking 2 missions ended in 1976 for another American spacecraft, Mars Observer, to set out for the Red Planet in 1993 September 1992. During this time, NASA shifted its focus from Mars to Venus, launching Pioneer Venus in 1978 and Magellan in 1989. It also conducted missions to explore Jupiter and the other gas giants, beginning with the Voyager mission in 1977 and continuing for 14 years with Galileo from 1996 to 2010. During this time, the National Aeronautics and Space Administration, NASA, launched 11 American rockets toward Mars. The newest component, the Mars Reconnaissance Orbiter, has a spatial resolution that is at least 10 times better than Omega on Mars Express. Both probes, set out in 1996, were successful beyond expectations. In particular, MGS continued to function for over a decade until communication was cut off on November 2, 2006. Amidst all the hoopla, a new plan was hatched. Once every 26 months, during a launch window, a small lander and orbiter would be sent to Mars. 1998, the first missions were the Mars Polar Lander, MPL, and Mars Climate Orbiter, MCO. In addition, starting in 2003, NASA will participate in an ambitious initiative with France and Italy to return samples from Mars to Earth, which will enhance the investigation of the planet. Regrettably, in 1999, the whole project fell apart. Launched the year before, 2 soil-penetrating microprobes, MCO and MPL, failed consecutively. Another setback occurred with the Mars program. For 2015 to 2020, NASA will concentrate on a more sophisticated exploration mission, postponing its sample return initiative. However, the momentum continued, and in 2004, after Mars Odyssey had entered Mars's orbit in October 2001, the 2 rovers returned to the surface and restored NASA's prestige with their outstanding accomplishments. See next page. Our next stop will be the Mars Science Laboratory, the Phoenix Lander, 2007, and the super satellite Mars Reconnaissance Orbiter, 2009, all of which blasted into Mars orbit on March 10, 2006. In late 1999, NASA's exploration program suffered a major setback due to the disastrous failure of the Mars Climate Orbiter and Polar Lander missions. However, this did not deter the crew. In June 2003, they outlined the secure and outstanding project requirements for the upcoming opportunity. In July 2000, the Mars rovers emerged as a solution. A mobile vehicle that can travel several kilometers is exploring Mars, equipped with scientific instruments designed for the 2001 lander instead of the established Pathfinder landing system. The original plan was to increase the chances of success by sending two identical rovers to Mars using separate launch vehicles. The problem was that the Jet Propulsion Laboratory at NASA had an unprecedentedly tight deadline of 3 years to complete extremely complex missions. Among the many challenges that JPL had to overcome was the need to make last-minute adjustments to airbags and parachutes while settling on a workable design. The rover's performance degraded with each test. On June 10th and July 7th, 2003, a weary crew watched as the two rovers were launched. We asked God to ensure the cars got safely where they were going. Was it feasible for them to work on Mars for 90 days? Spirit and Opportunity have continued defying expectations. Having traveled over 7 and 11 kilometers since their landing 3.5 years ago, their explorations of Martian crater floors and mountaintops have yielded some surprising results, the most important of which is the discovery of 2 new Martian locations with abundant evidence of the past existence of liquid water. On January 3rd, 2004, Spirit became the first rover to enter the Gusev crater. Everything proceeded as planned until day 18, when Spirit abruptly ceased speaking. The batteries were getting low because the onboard computer would turn on and off randomly. After a few days of worry and technical skill, the crew could fix the problem and focus on the January 25th successful landing of Opportunity. Luckily, Opportunity touched down inside a small crater, revealing the sedimentary bedrock for the first time. Despite its difficulties, Opportunity remained the preferred rover of researchers for a long time thanks to its exceptional location. It was stuck in a small dune for 5 weeks in the spring of 2005, while Spirit got back on the map by climbing the Columbia Hills, reaching an elevation gain of more than 100 meters, partially backward because of a broken wheel. The goal was to reveal more complex types of sedimentary rocks, shedding light on the unexpected geology of 2 separate Martian sites. In 2003, Europe launched a probe into Mars orbit, utilizing bolt-ons and collaborating on missions coordinated by the 2 nations. On Phobos 1, 2, and most notably Mars 96, the former Soviet Union specifically used European instruments. However, after the 1989 partial malfunction of Phobos 2, the loss of Phobos 1, and the November 1996 launch failure of Mars 96, a consensus was reached. European equipment would subsequently be used on missions in Europe. France and Germany evaluated the potential of a small satellite with Mars 96-like sensors after the disaster that befell that mission. In response to this idea, the European Space Agency, ESA, quickly developed a new mission, Mars Express. Mars Express was launched by the European Space Agency on June 2, 2003. It entered Mars orbit on Christmas Eve of that year. Researchers from France, Italy, Germany and Sweden are among the many European nations represented on the Mars Express mission. Despite their heated debates over mission goals, observation methods, and resource distribution, operations proceed smoothly. Exemplifying the efficacy of international cooperation in space exploration, Mars Express has transformed numerous aspects of Martian research through its advanced instrumentation. In the middle of the 1960s, the European Space Agency, ESA, began operations. Before the 1980s, Europe focused on exploring the solar system, shifting its emphasis from astronomical missions and studies of Earth's ionizing environment. Comet Halley was encountered by Giotto in 1986, and Huygens reached Saturn's moon Titan on January 14, 2005. The other terrestrial planets, including Mars, Venus, and Mercury, were relatively unnoticed simultaneously. Here, faint white curves represent the surface, and the white line at the top represents the planet's surface. European planetary scientists used Mars LS to explore the planet's interior and find long-lost craters. Interestingly, the probe designed these antennae to stretch when it reached Mars orbit in April 2004 after folding them accordion style at launch, with revised estimates indicating that the deployment could result in the antennae colliding and potentially damaging the spacecraft. They abruptly cancelled the procedure. Careful computer models of the maneuver were able to free the first section in early May 2005, 1 year later. The probe didn't run into any big problems, but the antenna tip was still not properly positioned. It was necessary to conduct further investigations, and the results showed that heating the antennae with solar radiation was crucial. Finally, the 3 booms were extended on June 17, 2005. The 30-kilogram Beagle 2 module was built by a British team specifically for Mars Express. Landing in Mars's atmosphere and analyzing surface materials with tiny sensors were all part of the Beagle 2 design. The father of evolutionary theory, Charles Darwin, served his naturalist apprenticeship aboard the first Beagle. Unfortunately, Beagle 2 stopped communicating after a successful cast-off, leading to the assumption that it had crashed. Her downfall disappointed many in Britain, where the little ship had gained a notable following. We still don't know what caused it. After the success of Mars Express, the Europeans wanted to expand their goals, so they launched the Aurora program in 2005 to conduct more exploration of Mars. The designers of Aurora understood that human involvement in Martian exploration could allow the discipline to grow beyond its current limitations and discover uncharted territory. Consequently, they involved specialists in ESA astronautics and the ISS in the project and used appropriate resources. Beautiful Aurora. In a few decades, astronauts may find ExoMars, the robotic emissary sent by the first Aurora program mission. Participation from an astronaut from Europe will serve as a symbolic confirmation of the program's success. The program aims to get Europe closer to 2020 regarding robotic probe exploration of Mars. The objective is to embark on a global human exploration of the planet. Venus Express is the second generation of the Mars Express spacecraft Point 1. The European Space Agency ESA considered building a similar spacecraft using the same technology as Mars Express, but at a much lower cost. What is the intended purpose of this spacecraft's journey? During the scientific community's consultations, a prominent proposal arose. Why not send Mars Express Mark II, stocked with almost identical instruments, to nearby Venus? The Venus Express was built in record time and launched on November 9, 2005. The Aurora program aims to develop the necessary skills and technology to conduct comprehensive future Mars exploration. Landing and deploying the ExoMars rover on Mars will constitute the first phase 2013. The goals will cover scientific and technological endeavors, such as studying the planet's habitability progression and looking for signs of ancient life. To reach rocks and soils untouched by surface processes, the rover will have a drill that can penetrate several meters. By analyzing these samples in a specially designed mobile lab, exobiologists hope to find chemical clues to the presence of early Martian life. ExoMars will use a radar instrument to guide the drill and detect ice deposits and geological layers. Studying Mars' habitability history is another goal of ExoMars, which aims to better understand the environment that future Martian humans might face. Attached to the descent module and operational for several years, the small geophysical and environmental apparatus, GEP, may accompany the rover to the surface. There may be a series of such stations on Mars, and this one could be the first. For the first time, state-of-the-art seismometers and other detectors will study the geological activity happening on Mars right now. Geophysicists, who remember the failure of Mars 96 and the subsequent abandonment of Mars initiatives by the USA and Europe, now await the Aurora expedition. ExoMars may fulfill a long-standing desire. Exobiologists, discouraged by Viking's unfavorable outcomes 30 years ago, also await the Aurora expedition. The geological diversity found on Mars is similar to that found on Earth. Examining this geological diversity will become the main challenge in the ongoing scientific investigation of Mars after its comprehensive structure has been mapped a few years from now. Biomorph colonies. How can we speed up the process of exploring Mars? Researchers at NASA's Jet Propulsion Laboratory imagine a solution involving colonies of biomimetic robotic explorers inspired by the natural world. Caterpillar tracks or winged seeds might guide these robots as they make their way to the surface. When alerted to a location of scientific importance, they communicate with one another, disperse to explore the world, and reassemble in force. The number and portability of the probes used will determine the outcome. To fully explore Mars's surface and subsurface, they must dig, fly, traverse, and communicate. They are planning several projects that sound like something out of a science fiction novel. The Martian surface is not an ideal place to find organic materials or ancient sedimentary processes because of the chemically hostile atmosphere and ultraviolet radiation. Digging is required. Consequently, to explore the surface's uppermost meter, the European Mars Express mission, 2004, used a mole attached to its lander, Beagle 2. Propelled by a spring mechanism, the mole, which weighed less than 1 kilogram, could move across sandy terrain at a speed of 1 centimeter every 6 seconds. After Beagle 2 had safely collected its sample, it would have retrieved the mole and its sample by drawing back the 3 meters of cable. Only then would analysis begin. Following Beagle's failure, see previous pages, NASA and ESA developed drilling technology for missions beyond 2010. One such mission is ExoMars. For the first time, instruments designed to monitor planetary surface heat flow on Mars will be able to be deployed during this succeeding mission, giving the tethered mole technology another opportunity. Mars's and Earth's polar caps store a wealth of information about their planet's climates. Cryobot, a robot designed to climb through ice up to several meters thick, is currently in the works at California's Jet Propulsion Laboratory, JPL. Its goal would be to study the different layers of ice as it comes across them. Aircraft can't fly through Mars's atmosphere unless they're 5 times faster than they are on Earth, or have bigger wings. Mars has an airlift about 100 times weaker than Earth's, and a gravitational force 2.7 times weaker. Instead of giving up, NASA engineers have built numerous prototypes. The 5-meter winged ARS spacecraft is one of these. It has the potential to fly 1.5 kilometers above Mars's surface, where it can take high-resolution images of Valles Marineris and profile magnetic anomalies. Another choice is helium balloons. The Russian Mars 98 mission was going to use a French-made balloon, but the plan was scrapped due to budget cuts in the Russian space program. A balloon was constructed by the French space agency CNES for the Russian Mars 98 mission, which was later aborted. The cylindrical structure of the balloon, which was made of 6 micrometer thick mylar film, contained 6,000 cubic meters of helium and measured 45 meters in height and 12 meters in diameter. A scientific payload weighing 30 kilograms and a balloon weighing 30 kilograms comprised 60 kilograms. Due to the lack of buoyancy on frigid Martian nights, the balloon is forced to follow its serpentine ballast line, also called a guide rope, as depicted in the figure. The wire would have conducted radar soundings on materials beneath the surface, using its antenna-like properties. Following the successful collection of lunar samples in 1969 and the following decades, see table, space agencies have lately considered bold plans to collect samples from other solar system bodies. The NASA Genesis expedition collected solar wind samples despite the spacecraft's crash upon return. After touching down on the asteroid Itokawa, the Japanese Hayabusa mission, ISAS Japan, faces a challenging return journey to Earth due to multiple subsystem malfunctions. On January 15, 2006, the Stardust mission of NASA successfully collected dust from Comet Wild 2. When will the Mars sampler be launched? There is a technical challenge with the return. Mars's gravitational pull is twice that of the Moon's. A low orbit can be entered with a launch velocity of 3.5 kilometers per second, and escape into space can be accomplished with an additional 1.5 kilometers per second. A small rocket and a maneuverable satellite could be used in tandem to send samples into orbit and then bring them back to Earth, according to one plan. A lot of gas will be required to complete all of these chores. When launching the satellite into orbit, will less fuel-intensive techniques like electric propulsion and aero capture be used? NASA is considering limiting the initial Martian samples to dust and air samples collected during a quick flyby. The SCLM mission, which was supposed to launch in 2007, never got the green light from NASA. Dangerous samples? A few secure labs will examine Martian samples in sterile environments reminiscent of the one where Apollo 17 astronauts stored lunar samples recovered in 1972. This method ensures that the samples are sufficiently isolated from the rest of the planet to rule out the possibility of harmful Martian life forms and protect them from Earth contamination. The SNC meteorites have probably been expelled from the deeper layers of the crust, but these extra samples would first be taken from the planet's surface. Evidence from more recent samples suggests that weather, water, sediment, and hydrothermal processes have all played a role in changing the surface material. They might even contain evidence of ancient Martian life. Furthermore, any contamination from Earth could have shielded them. What kinds of samples to focus on are the main questions that scientists ask. What are they looking into? Collecting samples from a site where lava has flowed would help determine Mars's history. Accurately counting meteoritic impact craters is currently the sole method for establishing relative chronologies. If you're looking for signs of life, you should look for sediment or an old riverbed. Mars has a record of its paleoclimates in its polar caps. Why not dig into one of them? A sufficient number of space missions will be required to obtain the necessary samples. Complex and demanding sample missions are likely to be in the works for years beyond 2015. It will take multiple launches, and the price tag for each mission could be more than €2 billion. If the National Aeronautics and Space Administration, NASA, the program's progenitor, continues to push for American astronauts to return to the Moon before 2020, it will be difficult for the agency to independently fund the program. The scientific community is strongly behind Europe's potential to play a pivotal role and even lead this new initiative. The continuation of the ESA Aurora program after ExoMars hinges on the political will of European governments to continue space exploration. Among the planets in our solar system, Mars is the only one that could support human habitation. Venus, our nearest neighbor, is home to a hostile ecosystem. Still, a lot of important things need fixing. Carrying enough fuel for the return trip becomes a major obstacle. The fuel cost of traveling from Earth to Mars would be slightly higher than that of traveling to the Moon, especially because the Martian atmosphere can slow down the spacecraft's descent in contrast to the Moon. However, more fuel would be required to return to Earth from Mars, due to the surface's stronger gravity than the Moon. Next, there's the divisive question of how long it would take to travel to Mars using conventional propulsion techniques. Each interplanetary mission would require at least 6 months. The amount of time astronauts spend on Mars is another factor. After touching down, the astronauts will have to wait for the next launch window, based on the relative positions of Mars and Earth, before they can begin their journey back. Typically, this means that you will spend around 500 days on Mars. Going around Mars would take more than 2 years. The vehicles used for these journeys must be robust and equipped with water and oxygen recycling systems to meet the crew's needs. In addition to the cancer-causing cosmic radiation and solar wind, the lack of gravity will gradually diminish the crew's physical capabilities. As a result, the preliminary endeavors were enormous. The Apollo program's designer, Wernher von Braun, envisioned a fleet of spacecraft weighing tens of thousands of tons in 1952. In 1989, President George H.W. Bush promised the United States a massive program to build spacecraft in Earth's orbit that would be over 1,000 tons in mass and use innovative propulsion technologies. Despite the many obstacles, there may be endless possibilities for research, exploration, and understanding of a parallel universe if humans venture to Mars. Will humans be able to travel to Mars in the next few decades? President George W. Bush officially assigned this far-off goal to NASA in January 2004, though Bush's initial objective was to set up bases on the Moon by 2020 rather than Mars. Building reliable launch vehicles and life support systems similar to those needed for a Mars mission is an immediate priority. But doing so could further extend the time it takes for us to establish our first foothold on the Red Planet. De Vaucouleurs analyzed all the observations of Mars that were known at the time, drawing on the state-of-the-art in planetary physics to summarize established knowledge derived from thorough examination. Upon re-examining the book 52 years after its publication, it became evident how inaccurate it was. The permanent atmosphere of Mars consists solely of nitrogen and a minor amount of argon, it says. Even though we now know that carbon dioxide makes up the vast majority of Mars' atmosphere. Although the actual value is closer to 6 millibars, de Vaucouleurs gives a range of 85 to 8 millibars for Mars' surface pressure. In a footnote, the author says, "We can now confirm that the polar caps resemble those on Earth, composed of frozen water. They say, we shall not dwell on a comprehensive examination of the reasons why the hypothesis concerning frozen carbon dioxide is no longer viable. This is true because the polar caps contain a lot of carbon dioxide snow. Mars presented difficulties even for the most brilliant minds in history. But instead of making fun of this revered author, we should learn from their experiences. Advanced remote sensing sensors have created a detailed map of the planet from multiple angles, and direct measurements have been taken from the surface of Mars. Despite the title suggesting otherwise, we have endeavored to consolidate the existing knowledge about Mars. We can say with absolute certainty that our book will be contentious. The findings from Mars Express and the Mars rovers have required a thorough revision of certain sections in less than 3 years between the initial and present versions. Time will inevitably disprove a number of the hypotheses put forth below. Are we showing signs of being negative? Nothing about us is gloomy.